Okay, we're good. All right, thanks everybody, and welcome to those of you in the room and on Zoom. I'm Charlie Kritzinger. I'm one of the co-chairs of Splashy this year. As you can tell, we're experiencing the joys of doing a hybrid conference at the moment. Thank you for bearing with us. We've got some time built into all of this for technical difficulties and all that. So if you're presenting, don't panic. It'll be okay. We'll fit it all in. So in this session, we're going to have one in-person talk, and then we'll have the rest are all going to be virtual. I think actually having all virtual is going to work pretty smoothly, but whoever that first person is that comes up there, I will give you some advance notice over the Zoom chat when it's time for you to start double checking your screen sharing and all of that stuff. So in addition to thanking all of you who are here, I should thank our program committee. So we had 8 members of the program committee in addition to Tien and myself chairing the PC. So thank you all for reviewing these papers, looking carefully at all the work that's going on in computer science education that we had a chance to look at. So, if you want to follow along with the Splashy program, there's a shortened link for this. I know you can find it on the Splash website, but this bit.ly /E21 link should work for you if you need to remember one. So, all right, with that, I think I'm going to hand things over to Len, who's presenting in person. Len, do you want to swap mics? You can present from anywhere you want. You don't have to stand up here.
Okay. So first I'd like to thank Grace Lewis, who's on the program committee, for calling this event to my attention. This is not part of my normal conference sequence. The most salient thing about me is that I'm probably the only person here with gray hair. You look around and everybody's young, which is good, but there's clearly nobody I know. So let me tell you, so I tell people that when you make a presentation, the goal is not so much to repeat the paper as it is to encourage people to read the paper. So this is that kind of presentation in Extrema. Oops. There we go. So I want to encourage those of you that have some input into curriculum to teach DevOps in the curriculum. I think without doing that, you're shortchanging your students. And this has been a passion of mine for about 10 years now. But it's fine, DevOps stuff are finally starting to appear in standard guidances. So if you know anything about where like the ACM IEEE recommended curriculum comes from, it's based on the SWBOC, the Software Engineering Body of Knowledge, which was last updated in 2014 and is in theory being updated currently, although that's been the stand. It's been real soon now for the last 5 years. So if you do a LinkedIn search and you look for various in the job category, computer science, if you search for computer science, you get 300,000 hits. The first half a dozen are for faculty members. If you search for DevOps, you get 114,000 hits. If you search for software engineer, you get fewer. And if you search for other things that I thought of, even less. So there's a tremendous industry demand for DevOps. And if you look at the first half a dozen DevOps entries, they're for managers. And so the idea is to build that capability in a variety of organizations. And so the demand is only going to grow. So this is not the first time I've stood in front of a group, although this is probably the smallest group, and pitched DevOps. In 2016, I organized a panel at CSEET. In 2017, I gave a workshop. at essentially CSEET. And the feedback I got in both cases was, we really should teach that, but we need materials in order to do that, because it's a lot of hard work to create a course. Okay. All of a sudden, it doesn't want to advance. Did I do something? Did you do something? Could you make it advance? There we go. And so in response to that feedback, there are now educational materials, and they've been shared with the Technical University of Berlin. So my co-instructor and I have been teaching this course now at CMU since 2015. So it's like 6 years. It was shared with the Technical University of Berlin, which are the other two co-authors, Ingo Weber and Richard something. And it's been shared with a third person. So she just joined the group in this semester. And these are quotes from her. So I'm enjoying teaching this class tremendously. It's a very popular class to register for. It was maxed out at the start of the semester. So all this is intended to show you that there's a great student demand as well as industry demand. And so let's talk about what DevOps is. What's the substance of it? Well, it's a set of processes intended to reduce the time between committing code and placing it into production. So if you look at the standard, and also to reduce the time to resolve incidents. If you look at the standard CS curriculum or software engineering curriculum, essentially it says, produce the code, check it in, and you're done. Okay. That eliminates a discussion of one of the most common sources of error, which is the part between the time you check it in and the time it goes into production. And it eliminates a discussion of how you fix errors, which is the reduced time to resolve incidents. So if you look at the DevOps processes, you start with the design. So some of the topics we deal with in the design phase are microservice architecture, how do you manage version skew? And if you don't know what some of these words mean, that's a good thing. That means that not only do you not know, but your students aren't going to learn. And so that should act as encouragement. So version skew is a term that you may not be familiar with. And then the next, after you've designed the system, you turn it over to the developers, and there's nothing about in DevOps particularly that has anything to do with the development process, except that the developers are the people that write the scripts. Okay, so one of the things about DevOps, the reason that it reduces the time to market is because there's a heavy reliance on automation. Automation, in fact, depends on two things. One is having a tool, and the second is having a script that will drive that tool. And so associated with each phase through the circle are a collection of tools. And what we do in our course is we expose the students to samples of these things. The intention is not that they're an expert in any of these tools. It's that they have some sense of what all the tool categories are. So there are testing tools, for example, automatic test. There are tools that manage deployment. The release phase is a reflection of the fact that some organizations have to have a human being before you release it. That's, I think, Sarbanes-Oxley. Okay. So something, if you have a human, then the human does that. The deploy phase, how do you actually put it into production? You're talking about multiple instances and so on. What happens when you operate it? You have to gather information. That's where the incident handling comes from. Something goes wrong. And then you look at the information that you've gathered during monitoring, and that may change the design. So that's just a quick view of the processes. That's not the flow of the course, but this is sort of an overview. So what educational materials are available? So learning objectives, content, course structures, textbook, assignments, rubrics, syllabus, everything you need, it seems to me, from an instructor's perspective. And so what are we trying to do? We're trying to build a community of people that teach DevOps. So far, it's the three of us that I mentioned. It's me, it's CMU, it's the Technical University of Berlin, and it's the University of St. Louis. But, you know, we welcome other people. And so the materials can get shared, different teaching styles. I happen to teach what's called the inverted classroom. I use that style, but other people have others. And if you're interested, ask to join DevOps Teachers. It's a Google group. And explain where you are in the process. Okay, so just student demand is high, industrial demand is high. There are intellectual things dealing with DevOps. You know, there's becoming a reasonable research literature. And the materials to teach the course are readily available. So the real question here is, did I convince anybody? Okay, questions?
Can we just shout out?
The hand mic is over there. But if you ask a question, I'll repeat it. Yeah.
Hi, I'm Doug Lee. I was volunteered into being on the steering committee for the next ACM IEEE curriculum recommendations, and you could at least be comforted that DevOps is definitely part of platform-based development in the next curriculum guide. So there's an existing category that was mainly for specialized platforms like gaming and web, as it turned out. They are now charged with putting something about DevOps into the ACM IEEE guidelines. And I am sure they are interested in your expertise, and I am going to connect you, whether you say, yes, I'd love to or not.
So my contact information is up there. The last association I had with the organizational activities was when Rich Hilliard was in charge of updating the SweetBox. I don't think he is anymore. And so that was 2 or 3 years ago. And at the time I was encouraging him to do DevOps stuff. And he said the issue was whether there was he agreed. And he said the issue was whether there was a separate DevOps category or it got rolled into other categories. And since then I've lost touch with him, and I've lost touch with the SweetBox. And I'm glad to hear that, that it is showing up in the standard guidance materials.
All right,
Yeah.
Thank you, Doug. I wanted to remind people who are asking questions, we can't see who is talking in the room, and I'm guessing you can't see all of us. So if you could announce your name when you start your question, that would be wonderful. But I did see that was Doug Lee. So we have one in the room here.
My name is Angelo. Going back to the slide where you had sort of the elements that you needed to, I guess one needs to teach for DevOps. You mentioned that you expose students to the various different tools that you need to know to I guess to carry out those particular tasks. My question is, for example, I know so the question is, do all of these areas have maybe principles, maybe not theories, but principles that students should know how to do this correctly, as opposed to just tools?
Sure.
I know for
I mean,
testing.
so what does a tool give you? If you use a tool that essentially forces you to use a particular process. I mean, if you have a compiler that forces you to put compilation in your process and then build. And so each tool has a process that it assumes, and the principles that we talk about in the theory part of the course are the processes and the assumptions that go into those processes. The other thing about tools is, at least in our course, all the tools are open source, or at least freely available. They may not be open source, but they're freely available. And so you don't need to spend any money to teach this course.
Thank you.
Are there any more questions online? I am not by a Zoom screen, but if there is one, go ahead. All right, I had one. This is Charlie Kritzinger from Grinnell College. Oh, I'm sorry, I didn't see your hand. Back here. Go for it.
Hi, I'm Paul He from the University of Pennsylvania. Just a quick comment about student interest. So we have these student-run courses at Penn.
So I can't quite hear you. Even worse. So Charlie, could you go interpret?
How about now? Is that better?
Yeah.
Okay, great. Yeah, so I'm Paul He from the University of Pennsylvania. We have these student-run courses at Penn. And just a note on the student interest, we have a few undergrads who are teaching this DevOps course. And they've made all the materials on their own. And the interest there is very high from both students taking the course and from these instructors who have made this entire curriculum on their own. So, yeah, I'll connect them with you afterwards, I think.
Great. Yeah, absolutely.
All right, we had one question on Zoom and then I'll hop over to you next. So Dennis asks, do you focus on particular continuous integration or continuous delivery frameworks?
So continuous integration is part of this. So the picture here is essentially the DevOps pipeline, or the left-hand side is essentially the DevOps pipeline. And so that's part of it. A large part is that at least the students that I deal with aren't familiar with things like IP address, with network concepts, aren't familiar with virtualization, containers and virtualization in general. So there's part of the course that deals with that. They're not necessarily familiar with security concepts. They know about security, but you know, how does TLS work, that kind of thing. So the course deals with that. The course deals with incident handling. So I would say continuous integration is a part of it, but I wouldn't say it's the overwhelming part of it.
All right, we have one more question in the room.
Thank you. Hi, I'm Pascal Amuso, fresh year PhD student at Purdue University. Okay, sir, so please I have two questions. The first, you mentioned that your teaching style is use the inverted classroom teaching style. I don't know if you could throw more light on how it helps your class or what it is. I could have Googled it too, I'm sorry. And then my second question is, so you have partners teaching from different countries, from TU, Germany, and you're at CMU. Is there any difference in terms of the focus of the class or the pattern of teaching, or like between teaching in Germany and teaching in
Okay,
CMU?
so this is a particularly interesting semester to get that question. So CMU has a campus in Africa. And so I'm actually teaching two sections of this as opposed to a hybrid. One section is for the CMU students in person, and the other is on Zoom for the students in CMU Africa. I would say that the students in person are a little bit better, but I think that has to do with the selection criteria to get into CMU. The cultural differences in the paper, Ingo and Richard talk about the differences between doing this in Germany and doing this in the US. So if you read the paper, there's a discussion of that kind of thing. Okay.
Thank you very much. Yeah.
All right, next up, we have our first virtual presentation. So Boyd and Howie and Martin are presenting their paper on ruggedizing CS1 robotics. We'll give them a minute to get all the screen sharing and everything going. Oh, that worked right off the bat.
Oh, great. All right. Good morning, everyone. My name's Boyd Anderson. I'm here to present our work, Ruggedizing CS1 Robotics, Tools and Approaches for Online Teaching. This is a joint work with Martin Hens and Hao-Wei T, who are both here today. We're all from the National University of Singapore, and we would like to talk to you about our experiences and technology for teaching CS1 robotics online. So before we get started, I need to give you a bit of introduction about the system that we currently have. In our CS1 course, we use an open source student-built browser-based IDE. It's called the Source Academy. And all of our student programs are written within a language called Source, which is a series of sub-languages of JavaScript. If you are interested in this Source Academy project, we have a few talks, any of the talks from the National University of Singapore today here at Splash E. So come and have a watch of some of those. Now, for our course, CS1 is a crucial component. Our CS1 course starts as a purely functional programming course. And the introduction of robotics happens at the same time. It coincides with the reintroduction of mutable state and assignment into our course. So the robots give us an opportunity to explore that. It also provides the students an opportunity to engage in group work, especially important when we're all doing online teaching, and also to see how their programs interact with and actuate the real world. And obviously, it is also quite fun. Our goal with our system is to basically have no impediments, that is technical or otherwise, to the students being able to apply their programming knowledge that they have gained thus far in the module, in the course, to control their robot. And to do so within this browser-based IDE. We don't want them to have to learn, say, Secure Shell or SFTP to transfer programs or anything to the robot. We are trying to remove all those sort of impediments so they can just concentrate on the learning. However, our previous system for robotics in the module, that is up until 2019, I had quite a few shortcomings and limitations that got in the way of this goal. So I'm going to hand over to Hao-Wei to talk about our new system and our old system.
Hey, is my slides on?
Yep.
All right, thanks.
Oh,
so,
we can see your presenter view. Sorry.
Let me try and fix that. Okay, is it right now?
Looks good.
All right, thank you. Our old system was basically Node.js with a custom library running on EV3Dev, right? And EV3Dev is a Debian distribution for the Lego Mindstorms EV3. So it's a very simple.
How your presenter view came back on now?
Oh,
I think
that's odd.
Oh, now it's gone. Yeah. Good.
All right, I'm just going to hide it. Okay. Yeah. So it was a simple solution. Built mainly using off-the-shelf components, right? And the benefit of it was that it was it was simple to create and required little maintenance, but it provided a rather poor development experience for our students. So if students wrote their programs on the computer, they, either in our web environment, the Source Academy, or in some other editor, they had to then, manually transfer the programs over SFTP to the robot, right? And alternatively, they could SSH directly to the robot and then write the programs using a NanoVim or some other command line editor. And neither of these were, particularly convenient or comfortable solutions, especially for students who are new to computing. And these form the majority of students in our CS1 course. So then after getting the programs onto the EV3, they had to execute it over the shell, right, over SSH. And, after executing, entering in the command to run the program, they would have to wait for about 10 seconds for Node.js to actually initialize before the program actually started running, right? And, because robotics inherently involves a lot of trial and error, right? Especially when, optimizing threshold values for sensor readings and things like that, this inherently just made the whole development experience quite frustrating. So before the pandemic, we used to hold sumo bot competitions every year, and a lot of time was wasted during the competition just waiting for these Node.js to initialize and programs to start up. So other than the poor edit run cycle, right, there were other issues as well, right? Because So because Node.js, or rather V8, which is the JavaScript engine that is underlying Node.js, drops support for our particular hardware platform, drop support for the hardware platform that the EV3 is built on, we were stuck on a rather old version of Node.js that did not support the particular, some of the JavaScript features that we used in source. And so this meant that when writing their robot programs, students had to essentially, switch language dialects, right, on top of all the other frustrations that they already had. And the fact that the whole experience took place outside of the Source Academy also sort of broke some of the immersion that we had hoped to achieve in the course. Students also had to figure out how to use SSH and SFTP. And while these were things that they would eventually have had to learn, the CS1 course we felt was not the best time for that. And this whole setup would have been quite troublesome to use during the pandemic when students could not meet in person to work on their programs together. Well, it would have been fine, right? It would have worked. The person who physically had the robot would have to be the one to sort of, transfer the programs onto the robot each time, and then, enter in the command to run the program every time they had a minor modification and things like that. And it would have been quite troublesome. Either that, or they would have had to sort of, figure out a way to remotely SSH into the system. So either way, it's not a great setup. So now that we've seen the issues with the old setup, which we could sum up as basically poor performance as well as inconvenience, let's look at the new platform. So the first component here is the Source Virtual Machine Language, which is a VM language that was designed as a natural compilation target for Source. So that means that Source statements and semantics translate easily into VM instructions, and the types of values in the VM also correspond exactly to the types in Source. The compiler we also wrote in TypeScript, and this is so that it could be integrated into the Source Academy easily, which is again a web environment. The VM language also includes facilities for us to expose platform-specific functionality to our Source programs. The next component is Sinter, which is our VM implementation. And we wrote it in standard portable C11 and designed it to be run on embedded platforms. So that means that we avoided floating point operations where possible, and also we avoided using dynamic memory allocation at all. And so these two components allow us to run our Source programs on embedded devices like the EV3, but we still need a way to get our programs from the our Source Academy onto the EV3 itself. And so this is where Sling comes in. The name is quite literal. It's a sling that sort of slings programs from our web environment to the our devices like the EV3. So Sling is a simple protocol based on MQTT, which is a lightweight publish subscribe protocol commonly used in IoT devices. In a nutshell, the web front end sort of sends compiled programs via the MQTT broker to the robot, which executes the programs and then sends the output back to the web front end. So by MQTT's nature as a publish subscribe protocol, we sort of get the ability for multiple users to connect to the same device at the same time for free. And status and output messages are broadcast to all of the connected front ends, so students can connect to the same robot at the same time. So with these three components, SVML, Sinter, and Sling, we now have our new setup. So this is how it looks like. Students first have to do a one-time setup by registering the robot with our web environment. And then after that, they can just connect to the robot via this panel on the right. And then after that, they can just develop their programs in the environment that they are used to, and then run the programs by clicking the same run button that they're used to. Right? Compilation is virtually instant, and the VM initialization is also instant by virtue of it being written in pure C. So no more manual file transfers or waiting 10 seconds for programs to start. And as a bonus, students also get the completion features of our online environment. So during the pandemic, our students could work together by just connecting to the same robot, and the student who had the robot simply had to connect it to the internet and maybe point a camera at it, and then they could collaborate over a video call. They could also use the collaborative editing feature, which is this session button up here, and it basically works like a Google Docs, except for this code editor over here, and they could then work on their program together live. Now I hand the time back over to Boyd, who will continue on to talk about the experience we had designing these assignments in a pandemic and the experience our students had working on them. Thank you.
Thanks, Howie. So we were very worried that we would lose our robotics component, that it was in danger during the switch to online teaching. And we still wanted to have the sort of the standard line follower and obstacle avoidance puzzles that are often in CS1 robotics courses, so that we can encourage students to explore the use of mutable state and assignment. However, we had to try and do this in a take-home manner. So our approach was to design puzzle posters and print these out, and big A0 ones, and one student would come and collect. And our module, however, has about 600 students and about 90 lab groups. And so as you can see from this trolley here, this was a lot that we printed, and the logistics was quite an operation to hand these out. So to summarize, we were able to have face-to-face sessions and online sessions. You can see on the left here, the face-to-face session, everyone is still socially distanced because they're still using their laptops to program it. They can do so in the same room. And here we're seeing an online session where one student points the camera at a robot, and all the students collaborate in a Zoom session. So in summary, our VM-based approach allows us to remove a lot of the impediments to programming the robots and improving that edit run cycle that Hallway talked about. Students can program the robots directly in their browsers, and we didn't have to sacrifice this robotics component. Indeed, during the year 2020, the feedback that the robotics component got in the module, in the course remained positive. And I'll end this talk with a bit of an advertisement and a bit of a call. Our tools are open source, licensed under the Apache license, and they're available on GitHub for you to use. And Cinta has been designed, it's written to be compilable using a C11 compiler. So any embedded system that you have one for that, you can use. And you don't need to use Lego Mindstorms for that. So here is our links here. Thank you very much. Sorry, we went a little bit over time. Any questions?
All right. Thank you. Are there questions in the room? We don't have questions in the room. Are there questions on Zoom? All right, I have a question for you. So this is Charlie Kritzinger at Grinnell College. I'm curious how much of this is specific to robotics and how much would be adaptable for other kinds of embedded development. Do you think this would work for an upper level class where someone is programming microcontrollers and they're not just using it as a platform to learn in CS1, but later on in their curriculum?
Well, we sweep a lot of the details under the rug. So I think for people who are learning to write, low-level programs or program embedded systems, this system is probably not as appropriate for that. But Hallway, what do you think on that?
Yeah, I kind of agree, because we really don't expose, like when you are programming microcontrollers or learning to program microcontrollers, you probably want to learn about the lower level details like poking registers and things, which all of these we sort of hide, because our main idea is just to expose the motor sensors and things like that. Yeah. But again, because of the way Cinta is written, you could definitely write expose registers directly to the source language, right? And then that would possibly work as well. But I feel like, I don't know, part of learning microcontrollers is also learning to deal with C and assembly.
The pain of microcontrollers. Yeah.
Fair point. Thank you. And thank you for staying up late with us. I've lost track of the time difference, but I know it's a stretch for you folks. So thank you very much.
Our pleasure.
Thank you.
Thank you.
All right. Applause is happening. All right. Next up, we have Eli Telovich. So Eli, go ahead and share your screen. All right, looks great.
Okay, thank you very much. So I'm Eli Telovich of Virginia Tech. So this is joint work with Yuji Ma, who was an undergraduate researcher in my lab, and he's since graduated, and now he is pursuing his master's degree at CMU in their Silicon Valley campus. So what is this work about? So this problem has long actually bothered me in some ways, because when learning how to code, when you introduce students in a particular language, I was always interested in how that language influences how students think about programming and how they learn their subsequent languages. And as it also turned out, so for a very long time, Java was the most popular language. Now with the proliferation and vast popularity of data science in the undergraduate curriculum, well, Python rules supreme in data science. So Python is also taught undergraduates, and also there is vast similarities between Java and Python. So, and that becomes a double-edged sword, because if you are introduced to programming in Java and then later you have to learn Python, what you can do, you can write Python like you would write Java. But for one thing, Python is much more concise than Java. And also it has very different programming idioms. So, just here's a formal problem statement. So Java programmers tend to, when they learn Python, then tend to emulate their familiar Java coding idioms in Python code. And there are some harmful consequences of that practice. So they introduce a non-idiomatic and verbose code of poor quality, and they use Python language features ineffectively. And as a result, their Python code becomes hard to understand and maintain by other Python programmers. Let's see. Okay, so what we have here is just a pilot study, so a standard disclaimer. So our findings are not definitive, and our insights are not conclusive. And there are a lot of threats to validity, basically to the study that we have conducted, and I'm going to point the threats to validity through the rest of my presentation. So what we did was very simple. So first of all, some background. Here at Virginia Tech, we teach our introductory computing sequence CS1 through CS3 in Java, and there is a lot of wisdom in that, because for a very long time, Java used to be the most popular programming language out there. So if you are preparing students for productive careers in industry, why not give the students the exposure to this language up front, so that by the time they graduate, they will have had 4, 5 or 6, depending how many years it takes them to graduate, years of experience in that language, makes them more competitive in the workplace, right? But now we also started teaching courses in data science, and the prerequisite for taking a data science course is to have completed our introductory sequence. So a student who's taking the data science course will have been introduced to computing into Java. Obviously, there could be some exceptions. The students might have learned programming in some other language before that, and so those are all threats to validity of the study. So what we did, we manually studied Python code, which was submitted in a data science course. And in the process, we've identified what we call 11 recurring verbosity patterns. And then we were wondering, so like, well, I mean, this is just an introductory course, so maybe students are still acquiring their programming skills. It's possible that this what we call this verbosity patterns will no longer be present once they start writing code for real. And in order to test this hypothesis, we analyzed several open source medium-sized Python projects for the presence of the same verbosity patterns that we identified in the code submitted in this data science course. Well, as it turned out, out of this 11 verbosity patterns that were identified, 6 were actually prevalent in open source projects as well. And then what we did, we just wrote up this 6 patterns as Java-like verbosity anti-patterns. Okay, just to give you an idea of what they are. So whenever you try to write something as a pattern or an anti-pattern, the most challenging issue is to come up with catchy names, and I'm not sure whether we've succeeded or not. So we tried to be, well, so maybe we were a bit verbose in identifying our verbosity patterns. So we kind of try to err on the side of being descriptive and easily understood than finding catchy names. So basically, these names of these anti-patterns can be definitely improved upon. Okay, so let me just give you a concrete idea of what we are talking about. So here's an anti-pattern example. And here's an explanation. So it's called modifying a list with an unnecessary if statement. So here we have a Python list, and then we would like to find the odd elements of this list. And if you were introduced to programming in Java, so a natural thing, so what you could do, maybe create an empty list, then write a for loop and just go through all the elements in the original list, then you would have an if statement inside the for loop, and then you would just append the elements that passed this task to the new list, and you would be done. Well, that's perfectly correct. You would get the desired outcome. Indeed, this odd list would contain the elements of the original elements that happen to be odd. But this is not how things are done in Python. So in Python, you write in one-liner like this, right? And for someone who is familiar with Python code, it's just much easier for them to understand, this logic than that logic. Okay, so here's another example. So Python has this nice feature where you can compare a value with 2 other values just in one swing like this, while if you are accustomed to programming in Java, you would do it with an AND statement. So, but the idiomatic way of doing this is actually as a one-liner like this. Okay, and one more. So Python has this really nice feature, negative indexing for arrays. So if you want to access an element from the other end of the array, you can just say a minus 1, while in Java, you would have to say a length minus 1. Once again, the same logic, but this one is implemented much more idiomatically. Okay, let's see. So what are the takeaway notes? So these verbosity anti-patterns, they're also present in open source code bases. And let me make it a point that Java is definitely becoming more concise in latest releases. I guess the language designers were shamed, by the advances in languages such as Scala and Kotlin and Python itself, and they tried to reintroduce some of these nice features into Java as well. A standard disclaimer: absolute conciseness is not always good. So the ultimate goal is readability and writing idiomatic code that others can actually understand well. So there is tons of related work that I'm not going to go into. So people really like to study how the first language influences students in their subsequent programming practices. And there are a lot of studies related to Python because of its great popularity. Well, and this is kind of my concluding slide. So I guess even though our focus is on conciseness, but it's only because Python tends to be more concise than Java. And in general, you know, one of the issues that we had with teaching introduction to programming in Java is that, you know, if you want to put hello world on the screen, you have to write public class, and then you have to write public static void main. How do you explain it to someone who's just learning how to program, why you need to write all this boiler code just to put hello world on the screen? So this is one of the criticisms of Java. So, but nevertheless, the point here is not conciseness per se. It's about promoting the production of idiomatic code, and we feel that we need educational interventions that specifically point out language differences and emphasize the importance of writing idiomatic code in any language, right? So if students have been groomed into thinking a certain way by their first languages, this differences between their first language and the new language that they're learning must be explicitly pointed out. So, and then we are continuing this research. I have another researcher working with me. So we are currently working on an IDE plugin that detects non-idiomatic coding patterns and suggests their idiomatic replacements. Let's see how much progress we're going to make. So I think I'm on time. You know, thanks so much for your attention. I'll be happy to take questions.
All right, thank you. We have a question here in the room.
Mhm.
If you have questions on Zoom, you can just put a note in the chat. I'll be sure to get to you when we have time. So.
Excellent.
Thank you. Yeah, it's a very good talk. So I have basically two questions. So the first question is, I think being conciseness is definitely good, but have you ever considered doing a user study to show the validity that like doing this, so like rewriting the programs with the automatic replacement will actually improve the readability of this code? This is the first question. The second question is that have you ever considered the performance related issues? So if you want to suggest the replacement, will it affect any kind of performance of the programs? Yeah, I'm very interested in these two questions. Thanks.
Oh, excellent. Yes, excellent question. So basically, so let me repeat the questions to make sure that I understood it correctly. So you're asking how the code being concise and idiomatic affects its reliability, basically, right? The bug proneness, if you like, right? That's the first question. And then the second question, how it affects performance, right? In terms of how efficient the resulting code is, right? So that's the question, right? Mm. Oh, okay, so let me try see what we have. So I think there is a reason why we are talking about, you know, code being idiomatic a good thing. So for one thing, so you know, if you write things in a prescribed, you know, kinds of fashion, so you are more likely to avoid bugs, right? You know, because for example, when you try, you know, to write a for loop, and this loop has convoluted logic, and there are multiple concerns intermingle inside this loop, so you are likely to introduce bugs than if you have a one-liner. And I think this is one of the arguments why functional programming is becoming so popular. When you can say just map, filter, reduce, done, right? And then if you try to rewrite the same logic imperatively, you know, you already wrote 15, 20 lines of code that are difficult to maintain, and to, well, depending how complex the original data structures, right, and all the other things, right? And then it also relates to the second question. So particularly in terms of conciseness, now programming is becoming increasingly more declarative. And when so one could argue that the actual performance, and by performance, we could mean many things: latency, energy efficiency, all the other things. And when your code is actually declarative and it's easy to grasp its semantics by, you know, that's what compilers and optimizers do for a living, I think they can do a better job optimizing your code for a particular runtime environment, and not just a compiled environment, but also just-in-time compilers, right? Where they can quickly grasp what your code is trying to accomplish, and it can quicker identify the so-called hotspots. So I think encourage students to write idiomatic code, which happens to be also more concise in the case of Python, is actually conducive to both reliability and performance in all its different aspects. Okay.
All right, we have one question in the room, and then I saw Elisa, you had a question on Zoom. So maybe I'll have you go last since your talk comes right after that. So we'll start with the question in the room here.
Okay.
Thank you, Eli. This is Rafi from CUNY Hunter College. Thank you for the nice talk. So as I'm reading your slides here, I'm wondering how much of the problem really is that, Python is allowing you to do things multiple ways. I remember when I learned Python, everything was like Pythonic, like, there's only one way to do things, as far as like, we're going to force you to do indents in a certain way, right? You can't like use curly braces and have not indent, for example. And I'm just wondering, like, is the root cause that, you have these different ways in Python to do these things, and whether, it's not really that you're the influence of your first language, but rather, these are kind of advanced features of Python, right? For example, like the negative indexing, and also like the, quite long for loop you had there in one concise statement. So I'm kind of wondering also, like, as far as students are concerned, like, how much of it is it advanced Python as well? Thanks.
Well, thank you so much for this great question. I don't think I'll be able to do your question justice, because the issue that you're raising is really complicated and complex in many respects. So it really refers to language expressiveness. Currently I'm teaching our programming languages class, and I had a big dilemma whether to teach functional programming in Scala or in some pure functional programming language, which doesn't allow any imperative ways to implement your program, right? And then I actually decided in favor of Scala, because I wanted students to learn kind of a commercially viable language, something that they would be able to put on their resume, and that would increase their competitiveness in the job market. But at the same time, it made my job as an instructor much harder, because when we said that when we're going to grade your assignment, if you deviate from the functional idioms, you're going to be penalized for that, right? While if we taught this course, while if the assignment were done in a pure functional language, we wouldn't have to worry about it, right? Because they wouldn't have been able to write loops, and they wouldn't have been able to mutate state, and so on and so forth. So I think whenever you have a modern language, it's always multi-paradigm, and it allows a lot of expressiveness, and it allows a lot of different ways to implement the same functionality. And so when you have choices, well, I mean, you have an option to make a bad choice. It's always an option, right? So the question is, should we take away these choices and say, use, that's the right way, and that's the only way that you can accomplish that? So I guess, there are some arguments that can be made in favor, pedagogical arguments that could be made in favor of that. If, for example, if I taught the entire course on functional programming, I would have started with the pure functional language, and maybe only later on introduced a multi-paradigm language, such as Scala, and say like, well, guess what? You can also use functional language to write the backend of Twitter. It's not just it's not just an academic curiosity. Functional programming, it's actually a practical tool. So I hope I've answered your question. I mean, I know it's not a satisfactory answer, but okay. So let me try to. So there are some questions from on Google Chat. So there's a question from Doug Lee.
I'm afraid we're a little low on time. I don't want to make people late for lunch here, so we might have to jump ahead to the next talk. Sorry about that.
Okay, so
but,
maybe.
But since we're all online, we can post these messages on Zoom or in the Discord and continue the discussion there.
Great.
Thank you very much, Eli. All right, next up we have Elisa, and Alex, presenting about the Liskov substitution principle.
Okay, can everybody see my screen? And Alex, you're unmuted.
Yes, can you hear me?
Okay, great. Okay,
We
so
hear you.
Alex and I will be presenting together. Hi, welcome to our talk. I'm Elisa Baniasad.
And I'm Alex Summers.
And we're here from the University of British Columbia, coming to you from the traditional unceded lands of the Musqueam, Tsleil-Waututh, and Coast Salish peoples. Today, we're going to talk about a new approach we're using for teaching the Liskov substitution principle, or LSP. What we propose is reframing the LSP through the lens of testing.
Let's remind ourselves what substitutability really means and go briefly over the LSP. Substitutability is a key SE and PL concept. When can one implementation be used in place of another without causing issues? This is relevant, of course, for software upgrades, for OO design methodology, for hot swapping components, etc. The LSP states that subclasses should always be substitutable for their superclasses. In this tiny example, we have a type good person setting a bird free out of a high window. That works fine if you're releasing a seagull from your window, but what if your subtype for bird is a penguin? Then throwing the bird out of the window is actually throwing it to its doom. Substitutability means that if you're expecting the bird to fly out of the window, a penguin is not a good substitute for a bird.
The LSP was originally broken down into a number of more specific facets called rules. The two most well-known and commonly taught rules are the precondition rule and the postcondition rule, which combine to be the methods rule. For a subtype to be substitutable, the preconditions shouldn't be strengthened and the postconditions shouldn't be weakened with respect to any corresponding specific behavior in the supertype. So a square isn't substitutable for a rectangle because the resize operation only allows a change in one dimension, narrowing the preconditions for resize. And a change in width will also change the height and broadening the impact of the resize. Similarly, a penguin isn't a good substitute for a bird if you're hoping it will fly. Its narrowed precondition is that it must stay on the ground, and its weaker postcondition is that you will have undesired deadly effects if you throw the penguin out a window.
Other facets of the original LSP are less commonly discussed and taught. The exception rule states that new exceptions cannot be thrown by a subtype's behavior. The penguin breaks this rule too. It throws the no way exception when fly is called. The properties rule is very general, stating that documented properties provable about supertype objects must also be true or provable for subtype objects as well. Exactly what qualifies as such a property is a little unclear, but examples certainly include object invariants, for example, constraining the observable fields in an object, or more complex properties such as history constraints about how those values may evolve over time. Once again, the penguin is a good example here. If the bird has a property, an invariant of staying alive, then throwing the penguin out of a window will not maintain that property of aliveness.
Oh, sorry, somehow I've gone into annotation and I can't figure out how to get out of it. Here we go. Okay, great. In our own experience and from talking with fellow educators, the many aspects of the LSP and substitutability are rarely covered in general. Instead, in order to somewhat simplify the LSP such that it can be taught straightforwardly, attention in software engineering courses is usually focused on the methods rule, comprised of the precondition and postconditions rule. The phrasing of these rules suggests a pleasing similarity to their requirements. One can be widened and the other can be weakened, which is often the emphasis in class. To make these rather abstract symmetrical requirements concrete, simple range-based examples are usually used, creating the analogy that ranges are allowed input values that can never be made narrower and ranges of output values can never be made wider. This appears to reflect the symmetry of the rules down to more concrete constraints on value ranges that students can latch onto. So we link the terminology back to the rule by saying that stronger means narrower and weaker means wider.
But then trying to get students to remember which condition is strengthened and which is weakened generally leads to all kinds of confusion and mental acrobatics. For instance, here's a snippet of a forum conversation from class.
I reasoned that class B can be a subtype of A if and only if class B is substitutable for class A. In order for this to work, B must have a stronger precondition than A. So since B has a weaker precondition than A, it is not substitutable for A, meaning B cannot be a subtype of A.
To which another student confidently replied in the thread, "Looks right to me." Of course, this is sadly absolutely wrong, and the students had the rule completely backwards. It seems that grounding these constraints in concrete value ranges doesn't necessarily help students to internalize the idea behind the principle itself.
So a few years ago, to get students past the which is which memorization problem, I came up with a smiley face visual device to help remember which is narrowed and which is widened. A smile is wider at the top and the preconditions can be widened. A smile is narrower at the bottom and the postconditions can be strengthened. Happy methods are substitutable methods. The opposite is true for frowns. While that helped students remember which is which, it didn't actually help them understand or anchor the spirit of the rule, that a subtype should be an acceptable behavioral substitute for its supertype from the perspective of the client. They still got confused about what wider and narrower actually meant, and would often apply seemingly good intuition to achieve the wrong result. Like, is the range 2 to 3 narrower than the range 5 to 100? It certainly seems narrower, it contains fewer numbers. But of course, that's not the point at all. If you're expecting something between 5 and 100, then a result of 2 will not cut it.
A further serious problem with teaching the LSP via these symmetrical constraints on ranges or tricks like this is that it conveys an intuition which doesn't always work for characterizing substitutability. For example, let's imagine a function in a class supertype, which guarantees you can call it with inputs 2 and 3, and that 2 will give the result 4, and 3 will give you some result in the range 30 to 39. Now let's introduce a couple of subtypes for supertype. Subtype wider domain provides a similar function that can also be called with input 4, producing values in this case somewhere between 40 and 49. Should wider domain be substitutable? Our range-based understanding so far suggests that broadening the possible outputs is forbidden. But in fact, adding new ways of calling a function will never cause surprises for a client, regardless of their output values in these cases, since a client will simply never call the function in these cases if they're working with this supertype. For this reason, wider domain is in fact substitutable. On the other hand, here's a second subtype, different relation, in which the guarantees for inputs 2 and 3 have been reversed. This type accepts and produces exactly the same ranges of inputs and outputs as supertype. Neither are widened or narrowed, and a range-based understanding would suggest that different relation is substitutable. But this is not the case. A client will observe behaviors outside of supertype spec if using different relation. Ultimately, the input to output relation provided is different, and so different relation as a class is not substitutable. This understanding of postconditions as partial relations is a much more precise underpinning, mathematical understanding of the LSP, but it's a much harder concept to teach with a smiley face or with ranges. What's more, students' real code won't only work in terms of simple ranges and will perhaps more closely resemble some of these more complex scenarios. That's a problem because they will very likely have trouble making the intellectual transfer from the overly simplified range or faces model to considering inputs and their corresponding outputs in general.
So we suggest coming at the LSP from a totally different angle, the angle of tests. Tests have the benefit that they're understood by students very early on in the curriculum. Students in most software construction or SE courses are taught early that black box tests are written to capture the specification of methods. In Liskov's book, she and her co-author wrote on object-oriented design. In the chapter specifically on testing, she says that a subtype's tests should include all the supertypes' black box tests. This implies, though it was never explicitly stated, that the subtype should actually pass all of the supertypes tests. And if it doesn't, then it's not substitutable. So to teach students the intuition about substitutability, in this work, we propose telling them if a subtype fails the black box tests for the supertype, it is not living up to the specification, and hence it is not substitutable.
Let's concretize this by revisiting the same two more subtle examples from just a moment ago. Let's start with writing tests that capture supertypes specification. We have one test for each clause in the specification, one that checks that 4 is indeed the output for 2, and one that checks that the output for 3 is within the specified range. To check whether wider domain is substitutable, we simply instantiate a wider domain object in place of the supertype and run the same tests on it. we can see that both tests pass. 4 is the correct output for 2, and the output for 3 will be within the desired range. All the supertypes black box tests passing means that for as much as we've checked of our specification, this subtype is definitely substitutable. The extra inputs accepted by wider domain are never exercised by these black box tests, so they don't complicate our analysis of substitutability at all. To check whether different relation is substitutable, we again instantiate, in this case, a different relation object in place of the supertype object and run the same tests. This time, the output for 2 is some value that's at least 30, which is not the expected output 4, and so the test fails. The test for input 3 also produces an output that falls outside the desired range, and so this test also fails. Any failing black box test tells us that different relation isn't living up to the promises made by supertype, so it isn't a good substitute for supertype and should fail the LSP. Note that by simply using the supertype's black box tests, we were able to correctly identify the unsubstitutable type with no knowledge of the formal rules or details at all.
In fact, black box tests are handy for capturing all the parts of the LSP. Well, almost. The post-condition rule is very easily captured. Tests can check the outputs and effects, so a failing test for an output or effect means a failure of the post-conditions rule. The precondition rules need a little bit of an assist to fail when appropriate. For an input to be rejected in the subtype, it has to be loudly rejected such that the calling test actually fails. This can be achieved a couple of ways, like by returning a value that's not within the valid range of outputs, or the method could throw a not acceptable error. The exceptions rule is very naturally captured. If a subtype's version of a method throws an unexpected exception, the test will fail. The properties rule, which is the rule that a subtype must maintain invariance of the supertype, is trickier in the face of aliasing, but in most normal cases, tests can be written that will check the properties. And this is a subtle point that would probably not throw off the intended learning outcome too far anyway. As we pointed out, previous work has also identified that the LSP actually ignores additional outputs as long as they're tied to new inputs. Our test-based approach captures that understanding of the principle as well. In practice, an inherited black box test will never execute the expanded range of the inputs in the subtype. And finally, accurately capturing the relation between inputs and corresponding expected outputs comes completely naturally from our test-oriented approach to substitutability.
When we tried this testing-oriented approach in practice in our own classes, we saw great outcomes. Students fared the same when faced with simple problems about the rule. We asked the same straightforward narrowing or widening methods rule questions as before, and also after teaching with this approach. Once using this happy, sad memorization technique that Elisa mentioned earlier, and more recently using this test-oriented approach that we propose here. Both times, around 80% of students got the question right, but observation told us that the students who went through the testing approach were far better able to discuss the concept of client expectations with relation to substitutability. Students taught the memorization technique were still confused by what constituted a range, whereas students of the testing approach were able to identify unsubstitutable types by virtue of their behaviors.
So to sum up, we propose that if we're trying to convey the broader concept of the principle of substitutability, then teaching it through the lens of testing is a better way. Students will be able to use their intuition for whether something is substitutable by assessing whether tests would pass or fail if run on the subtype. This gives students something concrete but still accurate with which to underpin their understanding, and that gets them a lot closer to understanding the spirit of the rule.
It also gives the instructor the chance to break free from simple ranges and other tricks into the world of more general properties and methods, illustrating a deeper sense of what it means to write substitutable and unsubstitutable classes. Thanks for your attention.
Thank you.
All right, do we have any questions in the room? There's one at the back here.
Hello, can you hear me?
Yes.
Okay, first of all, excellent talk. So my question is, I imagine there's a class of tests that look like they would break substitutability, but don't. The example that comes to mind is student testing, say, the function has 6 characters in the name, or say saying that if I call this function with 4, it raises an error. These tests that the student might come and say like, hey, I found this test showing it's not substitutable. How do you handle those cases and sort of explain to them that that doesn't really count as a valid black box test here?
So I think what you're referring to, and Alex, jump in anytime. I think what you're referring to are sort of tests that are tied to a specific implementation of the interface or the specification. Is that kind of what you're referring to?
Yeah, I think that's probably what I'm
Yeah,
referring
yeah.
to.
So actually, so those are in the paper, we kind of distinguish between black box tests and then glass box tests, tests that check the internals of the specification, those tests that you would write to improve your coverage or whatever. And those tests actually aren't inheritable by any of the subtypes. So when you're writing those tests, those are specifically supposed to be checking the implementation of your class. And those are not the ones that, that would render a subtype unsubstitutable. The only tests that that should be used for checking substitutability are these black box tests, the ones that only exercise the stuff that's on the packaging. So you wouldn't even test outside the range of the requires clause, for instance. You would exactly test perfectly, very politely within that range. Whereas in practice, to improve your test cover, you would definitely test outside. You would have some response for outside that range just to figure out how, because you would know how your implementation was handling it and you would want to cover those lines of code. But the spec wouldn't have anything to say about that. So your black box test wouldn't have anything to say either. So that's the message that we give students, is that it's not about, and actually it promotes this kind of nice hygiene about test suite development, that you are very, very cleanly delineating the tests that are about your specification versus the tests that are about your implementation. And it's those specification-oriented tests that can be inherited and that can give you insight into substitutability.
So just to make sure I understand this correctly, you're actually able to sort of turn this around and use the LSP to give students a better intuition for the difference between a black box and a glass box testing.
Yes, exactly.
All right, are there any more questions? All right, let's thank our speakers from our first session. We've got a bit of a break. Those of us who are here in Chicago get to go eat a box lunch. Everybody else, you're on your own for lunch. We'll see you back here at, let me get the exact time here, 1:50 p.m. Chicago time. So that's about an hour, 40 minutes from now. That is a good question. We don't know. The second session is all virtual talks. So what I will do for those of you who are, if you're sitting here getting ready to present in the second session, I'll leave the Zoom call running. It'll be not recording and muted. Things may be visible in the room, but you're welcome to sort of test out screen sharing and all that to make sure things are working. Just know that people might be in here seeing whatever it is that you're doing. So yeah, all right. See you back here in a little while. Thanks, everyone. All right, can people on Zoom hear me? I'm not sure I can hear you. Would someone who unmute themselves and talk?
Hello. Talking.
All right, great. Thank you. That worked.
Yep, we can hear you.
All right, great. So this is session 2. I am currently in an empty room, so it's all Zoom folks. So we will get started with our first talk from Yingji Fu about Pakon. So Yingji, go ahead.
Hi, can you hear me? Okay.
Yes.
So should I turn on the camera?
That's up to you.
Okay. I guess it's quite late in Beijing now, so I will not turn on the camera. Sorry, and let's start my presentation. Okay. Hi, everyone. I'm Minjie Fu from Peking University. My presentation will introduce our paper named PyCon, a symbolic analysis approach for tactic-oriented clustering of programming submissions. In the past decades, the enrollment in programming courses increasingly surges. The increasing size of classrooms poses challenges for instructors. For the quality of education in programming courses, instructors need ways to understand the performance of students. For example, it is important to identify the problem-solving ways in student submissions. In this paper, we also call the problem-solving ways as tactics. The importance of identifying tactics can be reflected in 3 tasks. First, it can assist instructors in achieving more efficient grading when tactic-related constraints appear in the description of assignments. For example, given an assignment that's finding the largest difference between any 2 elements in the given array while not using sorting. The tactic-related constraint in this assignment is no sorting. So in this example, the summation A, which used sorting to solve the problem, should not get 4 marks. To check such constraints, instructors have to manually inspect each submission, while with the help of identifying tactics, the efficiency of instructors in grading can be improved. Second, some existing tools for feedback generation require users to provide templates or reference solutions. However, it might be challenging for an inexperienced instructor to come up with comprehensive reference solutions in advance. By identifying tactics in correct submissions, these instructors can craft reference solutions with less effort. Third, identifying tactics can also help instructors to prepare targeted and adaptive teaching materials. For example, to find the largest elements in the given array, a good way is to divide and conquer, but some students may still use sorting or brute force. Having the view of distribution of tactics in student submissions, instructors can lecture to the class about the relationship between sorting and divide and conquer rates. So towards identifying tactics, in this paper, we propose a clustering approach named PyCon. The slides shows a motivating example and the desired result of clustering approaches. There are 4 submissions whose program implements the assignments of finding the largest difference. If we look into the tactics among these 4 submissions, submission B and submission C should be in the same cluster because they both compute the max and min of all elements. And submission A use sorting, submission D compares differences for all pairwise elements, so they should be put into separate clusters. We can see that to identify the tactical similarities in submission B and submission C, it is not enough to consider only the syntax of programs because the variable names and code structures of submission B and submission C are all different. So we should take semantic program information into account. In this paper, we propose a clustering approach named PyCon towards identifying tactics in functionally correct programming submissions. The input of PyCon is a set of functionally correct submissions, and the output is the clusters of these submissions. The whole workflow of PyCon includes 3 steps: test generation, path condition collection, and path condition-based clustering. Before we look into the steps, I'd like to first introduce pass condition, which is the core of our approach. Executing a program with a given input value can exercise a pass in the program. The pass condition for the given input value, we also call the pass condition for the The pass condition for the given input value represents the input constraints that all input values exercising the pass must satisfy, and the constraints whose satisfying input values must cause to exercise this pass. For example, for the program in submission C, the pass condition of the array 1, 2, 3 and the array 3, 5, 7 are the same. And the pass condition of 3 to 1 is different from the first two. We also notice that although there are local variables max and min in the program, they are actually not included in the pass conditions. Actually, the pass conditions reflect how the program of the submissions divides the input space into multiple equivalence classes, and the input values in the same equivalence classes should follow the same path, just like the array 1, 2, 3 and the array 3, 5, 7. Then let's look at the first step, test generation. The purpose of test generation is to attain tests with high code coverage, such as statement coverage, block coverage, branch coverage. Ideally, the test should comprehensively sample input values that can exercise different paths. So path coverage, we also call it path coverage. In this step, PyCon first generates the wrapper method, which can be regarded as a parameterized unit test for each assignment. Note that only one wrapper is needed for each assignment, and if there are some additional conditions of the input, instructors can add preconditions manually. After the generation of wrapper method, PyCon then use a test generator because it may be impossible to achieve full coverage of paths in a program. In PyCon, we adopt a structural test generator called PAX, whose default configuration is to generate tests with high block coverage. After the test generation, both the wrapper method and the generated tests are transferred into the second step, path condition collection. The purpose of the second step is to collect the path conditions derived from each test. There are also two modules in this step. First, considering that the generated tests for submissions are likely to be different, so PyCon first normalizes the test sets by union all generated tests. For example, in the previous example submission B, we got one test. There are two elements, both 18 in the array, and for submission D, we got two tests. They're all different. So after the union, PyCon also invokes PAX as a path condition collector on each submission with each test in the normalized test sets. PAX provides an API method for this task. For now, most of the preparation for clustering is done. In the step 3, PyCon does a pass condition-based clustering. The high-level idea of this step is to group submissions based on their equivalence of pass condition-based semantics. To be specific, for two submissions S1 and S2, the pass conditions of S1 and S2 must be equivalent in semantics for each test. Then we can say that they are equivalent in pass condition-based semantics. For evaluation, we raise 3 research questions. In RQ1, we want to know what is the number of clusters produced by PyCon compared with 2 syntax-based tools. In RQ2, we want to know how diverse is the syntax of submissions included in a cluster produced by PyCon. In RQ3, we also wonder what kind of tactics can be reflected by the clusters. The evaluation subjects consists of 2 parts. The first part is made up of correct submissions in the code hunt dataset. The code hunt dataset contains submissions from a 48-hour worldwide coding contest, and it is also used in many related work. Since PyCon can only work on submissions with correct functionality, we discard submissions whose behavior is different from the given solutions. The other part of the evaluation subjects consists of 66 sorting programs we collected from the internet. Sorting is a classical program taught in the CS programming courses. Among these sorting programs, we got 17 programs of bubble sort, 11 programs of heap sort, 16 of insertion sort, 10 of quick sort, and 12 of merge sort. As for the result, the purpose of RQ1 is to investigate to what extent PyCon can reduce the workload of instructors in expecting programming submissions. Ideally, with the help of clustering, instructors need to select only one representative from each cluster for inspection, rather than looking into all submissions. But if the number of clusters remains large, it is still burdensome for instructor to inspect all representatives. To answer this question, we count the number of clusters produced by PyCon and compared it with the number of clusters produced by ND and DF. As we can see from the table, in total, PyCon can produce a reasonable number of clusters, and the number of clusters produced by PyCon is much smaller than that of the 2 syntax-based tools. The purpose of RQ2 is to access the ability of PyCon to cluster together submissions with syntactic differences, but equivalent pass condition-based semantics. To answer this question, we assess the syntax diversity within each PyCon cluster. In particular, we measure the syntax diversity within a PyCon cluster at the number of syntax-based clusters that the submissions from this PyCon cluster belonging to. The syntax-based clusters are those produced by a syntax-based tool such as ND and DF. As we can see from the figure, PyCon can produce clusters whose syntax diversity is at least 2 for all assignments. Moreover, for sector to level 2, sector to level 5, sector to level 6, and so on. PyCon even results in clusters whose syntax diversity is greater than 10. In summary, PyCon can effectively group together submissions with syntactic differences, but equivalent path condition-based semantics. To answer the third research question, we manually check each PyCon cluster and summarize the tactics used in the submissions. The table shows the results of the example assignments, finding the largest difference between any two elements in the given array, while not, without, there's no tactic related constraints. Okay. We can see that there are 3 tactics summarized by the clustering results, and most submissions call the max and min API methods or implement the API method by themselves. This figure shows the clustering results on the sorting problems. The x-axis indicates the clusters produced by PyCon, and the y-axis indicates 5 different labels for the sorting programs. The number of programs is reflected by the size of scatters. As we can see from the figure, PyCon cannot identify common sorting algorithms, but the good news is that it can still distinguish whether a sorting program is stable or not. In summary, in this paper, we make the 3 main contributions. First, we raise the awareness of identifying tactics in student programming submissions. We also propose a symbolic analysis approach named PyCon for this towards identifying tactics. And we also conduct an evaluation on real-world data sets for assessing PyCon. Okay, that's all. Thanks for listening. Any questions?
All right, thank you. Are there, oh, we can clap in here. All right, are there questions in this room or questions on Zoom? I have a quick one. So I saw in the max and min approach, I should say who I am. This is Charlie Kritzinger at Grinnell College. So the max and min approach, you had 2 different loops. One was to find the max and one was to find the min. And I'm thinking a little bit about the path constraints. If those were written inside of the same loop, would it have the same set of path conditions? So like 1 traversal of the array rather than 2?
Yes, I think so. If they are written in the same loop, the path condition would not change.
So they have a sort of transitivity property to them that helps you group.
Yeah, I think so.
All right, interesting. Thank you.
Yeah, you're welcome.
Any other questions before our next group starts? All right, thank you to our first speaker. I guess this is the session of people who are in a time zone that is 12+ hours different from Chicago. So next up we have Martin and Boyd presenting.
All right, that's great. We are in the business of shrinking JavaScript. Can you see my screen and hear me?
We hear you, but not your screen.
Okay.
I muted you on accident, Martin. You might have to unmute.
Okay, unmuted and you can see my screen now, right?
Yes.
Okay, we are in the business of shrinking JavaScript for CS1. Your presenters here are Boyd Anderson and myself, Martin Hens, and this is joint work with Lokok Lim and Daryl Tan. We are from the National University of Singapore. A quick overview. After the motivation, I'm going to present 4 shrunken JavaScript dialects. Boyd will then talk about the implementation and the outcome. As a background, NUS started using the SICP textbook in 1997 in a CS1 course. SICP is the Structure and Interpretation of Computer Programs, a classic computer science textbook written by Hal Abelson and Jerry Sussman. And since 2018, this course is compulsory for all computer science first-year students at NUS. And that meant that we had to scale the course from originally 48 in 2012, when we started to use JavaScript, to 670 this year. Why are we still using SICP for CS1? Well, every department has their own reasons. We think that students benefit from SICP's emphasis on abstraction, as well as on the mental models for computation, rather than particular problem-solving techniques. Programming as communicating computational processes, rather than getting programs to run to solve problems on the computer. And finally, we have heard already earlier today the rise of functional programming in today's world of software. Of course, SICP was way ahead of its time, and we increasingly in the School of Computing appreciate a functional programming first approach. Why do we want to use a modern language such as JavaScript or Python rather than the original language in which SICP was written, Scheme? Well, we think that the transfer of knowledge is easier when the language is similar in syntax to the language that students will use in their later courses. And syntax matters. I think personally that Python and JavaScript programs are more readable than programs written in Scheme by and large. And if you don't agree with me down there, there is an email address to vent off your rage. Students' motivation increases when the language is obviously useful to them. We heard earlier today that students are looking for internships, you're looking for their first job and want to have something that makes sense to the employers on their CV. What do we mean by shrinking a language? We force students to use our sub-languages. And that means language features outside the sub-languages are simply not available. In our IDE, in our program environment, they just cannot do what, they cannot use those features. And why do we shrink a mainstream language for CS1? We think that for freshmen who are new to computing, the barrier of entry is lower when you start with a very small language, a minimalist language, rather than a full industry strength language that has, in the case of JavaScript, 800 pages of specification with tons of features, and every year with features being added. For us instructors, we can focus on the learning outcomes, and we're not distracted by constructs that are not conducive to the particular topic at hand. And finally, it is easier to implement tools for programming if the language is small enough. And in fact, all the tools that you have seen earlier today in the robotics, and you will see, are implemented by students in term projects. As an example, what we mean by shrinking the language, here you see what Eli called an anti-pattern. You see an equality test performed on a Boolean value. That is clearly overly verbose. We don't want the students to write these programs. And what we do is we simply restrict the triple equal operator to operate only to not operate on Boolean values. That can be done when you have the power to shrink the language. A more extreme example is that object-oriented programming is not introduced in our CS1 course or in SICP, and therefore our JavaScript sub-languages do not include objects. Here's the language progression in our CS1 course. The language that we start with is called Source Chapter 1. Source Chapter 1 is a tiny JavaScript sublanguage, just expressive enough to cover the first chapter of SICP JS, which is our JavaScript adaptation of SICP. It is the Lambda Calculus plus statement-oriented syntax, plus some primitive values, numbers, booleans, and explicit recursion. Source Chapter 2 is the language for the Chapter 2 of SICP, and it adds pairs. Source Chapter 3 adds variables and assignment for stateful programming. And Source Chapter 4 adds support for meta programming. Source Chapter 1 is the tiniest possible language that you may want to use in a course. It has just what you need to do purely functional programming, including constant declarations, function declarations. It is a statement-oriented language like any other mainstream language today. So it's a block-structured, lexically scoped language. And on the expression side, you also have nothing surprising. We have Lambda expressions as any modern language has. To give you an idea of how programming feels like in our programming environment, which is called the Source Academy, let me click on this link. Every program can have a URL in our environment, and the Source Academy is a web-based programming environment. So here you see the IDE coming up, and it is a program that uses our graphics library called runes. So you can stack two graphic entities together, you can put them beside each other, you can visualize them, and you can create a rune from a URL. So this is an example to create a rune from a URL. So if you click, you run the program, you see the splash URL that is in this, that is loaded from this website. And if you want to use assignment in this Source Chapter 1, that is a purely functional language. If you want to assign logo URL to some other string, you try to run this program. Sorry. You try to run this program, you see the error message, assignment expressions are not allowed in this language. So you cannot do you cannot venture outside of the language that we prescribe for the students. What you see is a little recursive program to give rise to a fractal pattern. So if you change the input number here, you see here the fractal pattern arising. You see graphically how recursion unfolds. So that should give you a little flavor for how programming feels like in this environment called the Source Academy. Source Chapter 2 then adds primitive expressions for lists and pairs. So data structures is the theme of Chapter 2 of SICP. So we add the null primitive expression in JavaScript. We add pair head and tail to mirror schemes, cons, car, and cutter, and we add a library for list processing. Source Chapter 3 adds constructs for stateful programming. So you see here the let declaration for lexically scoped variables, and you see variable assignment expressions. In our CS1 course, we also add while loops and for loops, although they're not used in SICP. We also add arrays in their minimal form, including array literal expressions and array access and assignment expressions. Finally, Source Chapter 4 introduces a parse function that allows us to do meta programming. And for the implementation, over to Boyd.
Thanks a lot, Martin. So you've seen this new set of sublanguages of JavaScript. How did we implement this? Well, we have our own programming environment that you've seen, the Source Academy. This is a open source project, mostly written in TypeScript and Elixir. And it has many learning tools, which I will go through some examples very shortly. But the most important part of it is that it is developed for students by students. This is a project which has around 150, our GitHub organization has around 150 people in it. And here is the current leadership of the Source Academy, and everyone but those last 4 names are just students. This is a student-run project. So let me tell you a little bit about the components of the Source Academy. So we have a parser. We use the Acorn parser. It's an open source JavaScript parser to build the abstract syntax tree of a student's program. And during this, we also check for any disallowed JavaScript syntax. So that might be things that we don't allow due to the source chapter language, the sub-language that we're using. And what we get out in the end is a valid source abstract syntax tree. The way that we execute the programs is not just to run them in the browser immediately. We require, because of the use of SICP, we require the ability to have proper tail calls. This is necessary for iterative processes in SICP. And although this is part of the ECMAScript standard since about 2015, only Safari supports this feature. So we have a transpiler that will detect and then implement proper tail calls using a trampoline function in our language, using a trampoline function, and then we evaluate that program using the JavaScript interpreter of the browser, the JavaScript engine of the browser, sorry. We have a bunch of different learning tools that have been built by students. For example, we have an algebraic stepper. This is actually the subject of the next talk. And I won't go into any much detail, but stick around and you'll learn a bit about that. We have a data visualizer. The data visualizer allows students to look at the data structures that they build in their program. They can look at pairs and arrays, lists and trees using this data visualizer. We also have an environment visualizer. Basically, it allows students to put a breakpoint in their program, and then it shows a picture much like this here, which follows the diagrams that are set out in SICP. It uses a continuation parsing style interpreter rather than the source transpiler that I just talked about. We also have some application domains. So how we get students to explore these tools that we've set out. The first one, if you watched my talk with Hawei, we have a robotics application domain. We also have a sound library. This sound library is the subject of a talk in the 3rd session today. We have a curves library, which allows us to do a kind of curve drawing. And we also have a video processing library as well. We've had some pretty good student feedback. So in the last year, last time we've run this course, 91% of students had said they agree or strongly agree that the Source Academy, our tool, helped them understand the structure and interpretation of computer programs. And indeed, Martin was saying before that we had scaled this module up from having around 100 people all the way up to now 670 people. And you can see here that that black line is the number of students in the module. You can see the moment where it went from being an optional module to a core, an optional course to a core course. And you can see that there was a little bit of a dip in the first years of scaling up, but we're now back up to where we started again, back out of that valley. Students seem very positive on the course. So to summarize, shrinking this CS1 language is liberating to everyone involved. To the students, it kind of levels the playing field. They can achieve what their expert programmer peers can achieve. They're not, even if they come into the CS1 module with no programming experience. For us instructors, we don't have to worry or sweep under the rug any language features that we're not prepared to talk about right now or don't suit the topic that we're talking about. And for implementers, as you saw, all of these tools that I've shown you, the Source Academy itself, these are generated by students, produced by students during term projects. So implementers can design and implement new tools. And our outlook is very positive. The design of the Source Academy allows you to just pull out JavaScript and plug in sub-languages of, say, Python or Java or C with some effort or even Scheme. So fork it and try. The link is right here. And that is the end of our talk. Thank you very much.
Sorry, I think my mic died. Is that working?
Oh,
yes.
We can hear you now.
Now it's not working.
Yeah.
Can you hear me?
Yes.
Okay. Should I
have this ready.
Sorry, we're unable to hear it on our side.
Sorry, can you hear me now?
Yes.
Yes.
Great. So yeah, I just want to say, first of all, thank you so much for the talk. That was really cool. I especially love this summary slide about how it liberates those different classes of people. One question that I had is, have you considered sort of extending this to the type system? So I noticed that, this is implemented in TypeScript. So I was curious if you had any thoughts about having these sort of like language levels at the type level.
Yes, that's a great question. I also attended a session yesterday where this question came very prominent in my mind. The SICP, of course, is using Scheme, dynamically typed language, and types don't play, explicit types don't play a role in SICP. But my co-adapter of SICP JS, Tobias Rickstadt, and I, we are thinking of developing this material further, and typing is indeed the candidate for the next chapter if we would ever write it. Definitely. And indeed, reflection of types. That's definitely an area to cover, especially for students, to be able to see the power of types in today's programming environments.
All right. Oh, we got another question. Okay.
Hello, my name is Braxton, and my question is just, so this is being a CS1 course, and of course, there are often students coming in with varying levels of experience. Do you get any kind of pushback from students who say, I want to use mutation here?
Yes, actually, that's what we see quite a lot with students. About 30% of our students have significant programming experience. And for them, the first couple of weeks are frustrating, for sure. But that type of frustration, I think we're willing to accept in exchange for the benefits that you see on this slide. and they come on board, especially today when it is getting better and better because functional programming is becoming more and more mainstream, and they are motivated to learn functional programming, even though they come from a background of 10 years of JavaScript programming, the entirely imperative style.
Thank you. Thank you.
I just muted myself. Okay, so this is Charlie. I'll just add students do that for Scheme too, so there's nothing new there.
Yeah, sure.
Dennis, did you want to ask your question, or would you like me to read it?
I can ask it. One of the problems is that everybody's at the beginning focuses on introductory computer sciences learning programming, and actually some of it is actually learning how to do design thinking. And I'm wondering how much having the constrained language may actually help people, you know, take a step back and say, oh, I actually have to design this thing.
Yeah, that's a great question, but I think there is the emphasis of SICP, of our approach, is still programming in the small. There is no real, SICP doesn't really teach problem solving, doesn't really teach designing solutions. It has a wealth of very good examples of well crafted programs, but it doesn't teach how to program. So the emphasis lies more on abstractions and on the mental models that arise when computer programs run. So the emphasis is different. We have then follow-on courses that go into algorithms, design, and then eventually programming in the large and software engineering and software design. But you can try. It's not in the scope of our course to go into those design areas, but it would be interesting to see, how you can constrain students effectively for the purpose of following particular design principles.
Yep. Thanks.
All right, I think we should head on to our third talk in the session. So we're going to hear a little bit more about the stepper.
Okay, hi everyone. Can you hear me?
Yes.
Yes.
Okay, great. So let me start. I'm Yi Jian. Okay, hi everyone. And together with Peter, we'll be presenting our paper on the stepper, which is a step-by-step evaluation tracer for the source2 JavaScript sublanguage that you saw earlier. So I will begin with explaining the core concepts behind the stepper, and Peter will later demonstrate them in action. Okay, as you heard from the previous talk, the SICP textbook is used for CS1 in the National University of Singapore. But instead of using Scheme, okay, we are using the source sublanguage. One characteristic, as mentioned, right, is the emphasis of SICP on the different mental models. In particular, in the first half of the CS1 course, we focus on the substitution model, which is a simple algebraic reduction method. Okay, it is a purely functional reduction method. So the stepper is implemented on this functional sublanguage, source2, which made the stepping possible. So let us see what this the substitution model is about with a simple example. So consider this source2 program, which is a valid JavaScript program, on the square function. Okay, before we start, it is important to mention that in the substitution model, there's no idea of a naming context or environment which stores the definition of names. Okay, all references are resolved by directly substituting its definitions when the declaration is made. So in the first reduction step of the substitution model, the definition of the square is first substituted into all function applications in the rest of the program. Then reduction goes on intuitively from left to right, first substituting 2 into the lambda function, and then substituting 2 times 2 with 4, and similarly for the function call on the right. Finally, we arrive at 13. Now that we have a rough sense of how the substitution model works, let us look at a crucial detail before looking at the stepper demo. If the function's body block only has a single return statement, like here, the substitution is simple. We just need to replace the calls with the return expression. However, in source, the body of a function declaration is allowed to have multiple statements, which might contain important information that cannot be omitted. Suppose we define the square function this way, a little differently. And in this case, we cannot naively substitute the applications of square with just the return expression, which is x arrow result. This will make the program, okay, an invalid evaluation, okay, making result a free variable. Therefore, to deal with this program, we introduce the idea of blocks at the expression level and the display of the stepper. So instead of just substitute the names with the return expression, we substitute the whole body block instead. This will result in blocks at the expression level during evaluation time, okay, as opposed to only at the statement level for JavaScript. Okay, now that these blocks capture enough information, how can we extract the return value from it? So the reduction of block expression is nothing out of the ordinary. We'll look at the first statement in the block and reduce it repeatedly. Here we see that the first statement is reduced and a constant, okay, which carries the result, the value of 4, is substituted to the return statement. When the first statement of a block is a return statement, the whole block will then be substituted by the return expression. In this case, it is substituted by the number 4. And that's all for how block expressions work. Now, let us have Peter to show you what this looks like in the stepper with a live demo.
Thank you so much, Yijian. I would now like to give a very quick demonstration of the stepper in the Source Academy that was showcased a while back, which is the online learning environment used to write and run source programs. So without focusing too much on this specific program just yet, I would like to guide you through the core functionalities of the stepper first. The stepper interface can be loaded by entering a valid program in the text editor on the left, like so, selecting either source 1 or 2, as they are the versions of source that are supported by the stepper, then switching to the stepper tab on the right and running the program. The tool provides a random access slider to move to any specific moment during the evaluation of the program, and also single step buttons to more readily visualize the evaluation process in a step-by-step manner. You may have also noticed that different parts of the program are being highlighted as you traverse through the steps of evaluation. This highlighting indicates the expression or statement that is to be reduced, aka the regex. Even numbered steps highlight the regex in red, representing the regex before reduction, whereas odd numbered steps highlight the regex in green, representing the regex after reduction. For every even odd pair of steps of reduction, a brief explanation is given below that explains what type of reduction is being performed. Now returning to the program, this specific one, a function square is defined that accepts a value, internally declares a constant that is the result of multiplying said value by itself, and then returns the result. The steps through which this program is evaluated can be effectively visualized with the stepper. The stepper encounters a function declaration statement on the first step of evaluation, consequently substituting all occurrences of square with the function square. When square is called with an argument of 2, the call expression is reduced to the body of the function square, where 2 has taken the place of the parameter x. This is an instance of an expression level block arising during runtime when a function with a body that contains multiple statements is called. The binary expression 2 times 2 is reduced, from which the result 4 is associated with the name result in the constant declaration. Once all occurrences of result are substituted with 4, all that remains is a return statement that effectively reduces the block to whatever value is being returned, in this context, 4. The same steps of evaluation occur when calling square with an argument of 3, ultimately returning the value 9. The evaluation of the program is then run to completion with one last reduction of the binary expression 4 plus 9 to the value 13. This example clearly demonstrates the occurrence of expression level blocks during the evaluation of programs that involve function bodies with multiple statements. Now that the core functionalities and the reduction process of the stepper have been covered, I would like to take a look at a more interesting example that involves explicit recursion. In this example, after reduction of the function declaration of factorial, all occurrences of the name factorial within the body of factorial itself and the call expression are substituted with the function factorial. When calling the function factorial, notice that no expression level blocks arise as it did in the previous example. If the body of a function consists of just a return statement, the stepper directly reduces a call expression to the expression that is to be returned. From here on, reduction is performed as usual. The predicate of the conditional expression reduces to false, effectively reducing the whole conditional expression to the alternative expression. Before another call to factorial, the argument 4 minus 1 is first reduced to 3, from which factorial is called again. This process repeats until the function factorial accepts a value 0 and terminates, ultimately collapsing all deferred operations at the end. Although this example is fairly simple, there exist other programs where a recursive call to a function can lead to hundreds, if not thousands of calls of thousands of steps of evaluation. This is where the special function skipping feature comes into play. On steps where a function call occurs, a learner may click on either of the double arrowed buttons to skip between function calls, simplifying the steps of reduction. This way, a learner can decide to skip over parts of evaluation they think are unnecessary to better visualize the overall behavior of a program. Now, for the last example, I would like to delve a bit deeper into the different iterations of source, specifically source 2. So if you recall from the shrinking JavaScript talk, source 2 is different from its predecessors in that it introduces the pair and consequently the list data structures. This example involves the map function, which is a function that accepts 2 arguments, a unary function and a list. The function returns a new list that contains values that are the results of the function application on the values of the input list. The function declaration of map is handled similarly to previous examples. Before calling the function map, the second argument must first be evaluated to list form as per applicative order reduction. On the first iteration of map, the input unary function and list are substituted into the body of the function for each occurrence of f and xs respectively. The predicate is evaluated to false, reducing the whole conditional expression to the alternative expression. Now here, to call the function pair, its arguments must first be reduced to their simplest form. This inspires a call to the head function, which retrieves the head value that is 1 and passes it into the anonymous squaring function. The call to the anonymous squaring function is then performed normally with an argument value of 1, returning 1 times 1, which is in turn reduced to 1. This process repeats for every value in the input list until termination, collapsing all deferred pair operations at the end. Now, with these examples covered, I'd like to pass it back to Yi-Jian, who will be discussing the implementation of the stepper in even greater detail. Yi-Jian.
Okay, thank you, Peter. So let me share with you in this section an interesting challenge when implementing the stepper. Okay, but before that, let us have a refresher about Lambda Calculus. In Lambda Calculus, there are variables such as x, y, and z, and abstractions using the lambda symbol, represented in JavaScript as an arrow. We can think of a lambda function as an anonymous function. When supplied with an argument, it will return the part after the arrow, substituting the parameters with the supplied arguments. In this example, we have a function x arrows xz applied to y arrow y as an argument. The reduction here is called the beta reduction. The x in the body will be replaced by the argument y arrow y. And in the next beta reduction, the y in the body will be replaced by the variable z. In short, beta reduction reduces function applications by just replacing the parameters in the body by the arguments supplied. Now that we know beta reductions, we can view what we saw in the demo just now with a different lens. Let us use the same factorial example in the demo. This definition uses explicit recursion, which is seen by the factorial call in the definition. To evaluate, we first substitute the occurrences of factorial in the rest of the program, getting the top right box. After this beta reduction, we replace all the variables n by the number 4, finally reaching this step. To the students, at this step, the name factorial is magically expanded into its definition again. But remember that the substitution model does not have a naming context that stores the definition. So therefore, we have actually lost the definition of factorial after the beta reduction step, resulting in a free variable factorial. This is an invalid program now. In our implementation of the stepper, we asked the question, is there a way to resolve this problem of explicit recursion without using a naming context, staying true to the spirit of substitution model? And the answer is yes. The solution to this problem is the mu term, analyzed by Ariola and Klopp in their 1997 paper. And we just take the same technique for our stepper. In short, mu terms are just lambda terms, but with a more interesting reduction rule. Let us see more in the next slide. During the reduction of mu terms, we need to do two things, other than substituting the arguments into the body with the, like the beta reduction in lambda calculus. You also substitute the function name with the mu term itself. That way, the recursive definition is preserved for another round of recursion. Let us see how this would work in our factorial example. After going through the mu application reduction here in red, the block expression is reduced and the block is discarded. Here the ternary operator is evaluated, and in the alternate, we have another mu application. But this time we know that it will preserve the definition. Finally, it will reach the result of 24, and we have an explicit recursion without a naming context. We have all the gory details about mu terms and block expressions, including their reduction and introduction rules. In case you are interested about them, you can find them in our paper. Before we end, let us look at how the stepper saves space. The main concern of implementing the stepper in a web app is that the thousands of steps will take a massive amount of memory storing abstract syntax graphs in our case, so rendering the Source Academy application unusable. So we take an approach to maximize the sharing of syntax graphs in every step. In our implementation, for example, these 4 steps will share a massive amount of structures across them. For example, the function declarations are shared, the mu terms are shared, the lambda expressions are shared, as well as the list data structures. This makes the application extremely space efficient, since almost all the syntax graph nodes are shared. To summarize what we have seen in our presentation today, we have covered new features such as blocks, expressions, and mu terms that are introduced to help build stepper as our source of truth when it comes to the substitution model in Source. Since its birth in the summer of 2019, we have been using it in class for the 3rd year. I was the first implementer of the stepper, and throughout these years, there have been batches of students, such as Peter, who implemented most of the new features such as redax highlighting and function skipping. The stepper is now an indispensable part for teaching CS1 in NUS, by the words of our coordinator, Professor Martin Hans. If you are interested, feel free to head over to sourceacademy.org anytime to try out the stepper. Thank you.
Thank you very much. Are there questions in the room first? Yeah.
Hello, this is Braxton again.
Hi.
Firstly, this is really cool. Uh-oh, can they not hear me?
I can
Am I
hear you,
audible?
yeah.
Oh, okay, we're good. My only question is, some of the intermediate steps in the stepper produce programs that aren't valid source 1 or source 2 programs, I think. And I wanted to know what were student reactions to that? Was there confusion at all?
Okay, maybe the prof can chip in on this.
No, I want to pass it back to you guys. You are the students. So Peter, you took a course and we already had the stepper, right? So were you surprised to see blocks at statement level, at expression level? Sorry.
Me personally, I don't think I really knew like the significance of expression level blocks at the time. I thought they were treated sort of in the same way, but now that I've worked on it, like as a team, I see that it's an implementation that is specific to the stepper, and it's yeah. So at the time, I don't think I had that big an issue with it though.
Okay.
Yeah, I think mainly the students see it, but I think they come to accept it that although they see it, they can't write it in their code.
Yeah, that's right.
So it helps with the understanding of the evaluation rather than being a syntax feature available.
All right. Hi, my name is Will. And my question is about, in the 3 years you've been using this, I'm just curious, what kinds of insights or mental models or cleared up misconceptions do you think have been most driven by the use of the stepper? Like, what are the specific things that students, come out after having stepped through an expression with this tool and been like, that's clear to me now?
Yeah, I think I can answer this. SICP isn't going to the extreme details in the substitution model. Their focus is on function application and basically function application as the core of the substitution model. Whereas we take it all the way to the micro steps. So conditional expressions, arithmetic expressions, they're all now explained within the same model. And I think that helps the students. They see this not just as a conceptual tool to understand function application, they see it as a way to visualize what happens when these functional programs run from the beginning to the end, from the actual program that they enter in their IDE all the way to the final result of the program. It's all a complete step-by-step process for them. And I think that's the added value over SICP and over other functional programming first approaches.
Hi, can you hear me?
Yes.
Okay. My name's Logan. This is a wonderful talk. Thank you. I had a quick question, particularly because the granularity of the visualization is something I found really fascinating. When you're calling a function as a part, like during the expansion of the evaluation, it doesn't seem to show the part where it like substitutes the formal parameter with the value. And I was curious why that decision was made, just to omit that step.
To substitute the form parameters with the values. That's what is happening in the stepper. I
think, or maybe I can say a few words on that. I think it was hidden in one of the steps to the students. So they will only see that the definition of the function is substituted into the name, and then in the next step, they will already see the arguments being passed into the body of the function. So I think it was a conscious decision to hide these details. Yeah, to keep it clear, because the students will already know that this function is actually related to the function that I have defined before. So we just show them the substituted result instead.
Okay.
Because otherwise it will cut out the so it's like kind of a design decision.
Yeah, thank you so much.
Okay, thank you.
One more question, then we'll have to let our last talk in the session get up. Maybe I'll have you start doing your screen sharing and all that while the question is going.
Hi, my name is Slim. Thank you so much. This was like really, really excellent work. One thing I'm curious about is in practice, how complex of or large of a program can students typically write before the stepper becomes essentially intractable to comprehend the output of at its like densest stage, whether that's just like the sheer number of paired delimiters piling up at the end, or like lots of expressions and they can't really keep track of where's what. And then I guess a corollary to that question, since I'm restricted to one nominal question, is I guess, have you kind of like what Logan just asked, have you experimented with different settings that will abstract over individual like small steps, more or less? So for instance, you might show alpha conversion explicitly in one version, and then another might show function application just like from, the fx form, and then by the end it's just reduced to whatever the body with the substitution and stuff looks like. So I guess, have you experimented with like different configurable levels of black boxness?
Yeah, the alpha conversion is very rare in our case. We usually don't need to do any renaming. Then regarding the granularity, the big steps that Peter showed is our only tool at the moment to go in larger steps. So we can go on the function level if you go to the next call of the same function. But you're right, we would, to analyze larger programs, we would need to take this idea further and see maybe, but you're very right in saying that the whole approach becomes quite practically intractable when you deal with really complex programs. So I think the value of the stepper lies in the formation of this mental model, rather than the actual analysis of complex programs. And there we do have another gap. So what do students do to debug purely functional programs? In SSCP, SSCP doesn't have an answer to that. We would need to wait until later mental models to have better debugging tools. At the moment, we're sort of stuck with that micro level Lambda Calculus style reduction. No real answer to this at the moment.
All right, thank you very much. So we have our last talk in this session. Yusuf is going to be telling us a bit about compiler construction. So Yusuf, go ahead.
Sure, yeah, can you hear me well?
Yes.
Great. All right, yeah, hi, I'm Yusuf. And today I'm going to share with you our experience teaching a compilers course. So last winter, we taught the graduate compilers course at UC San Diego, and we knew a few things going into the course. We knew we had about 50 master's students enrolled in the class. We knew the instruction staff would consist of Joe and myself, and we knew the course would be offered remotely over Zoom. And we had a vision for what we wanted students to build in this course. We wanted them to build a compiler where they can just fire up their browser like this and use a web-based editor like you see on the left here to write a program, and then maybe they can compile it and run it in the browser. And from there, they can use a REPL to interact with the program that they defined. And the students actually did it. This is the compiler that our students built. And it does a whole lot more than just printing /E. The compiler has a lot more features than we would typically assign our students. And that's because the whole class collaborated on it. And to get us to a place where we could all collaborate on building this compiler, we wanted students to learn some core compilers topics. This is why we structured the course to be in 2 parts. In the first 6 weeks, the students worked individually, implementing core features like numbers, functions, classes in their individual compilers. And then in the last 4 weeks, we all came together and started contributing to the same code base, adding various features like strings, lists, closures, memory management. And in the end, we ended up with this compiler that supports a lot of really interesting features. We really enjoyed this experience and we learned a lot from it. So in the rest of this talk, I'll dig deeper into the infrastructure we used for this compiler and how whole class collaboration worked. So let's begin with the infrastructure we relied on for the duration of this course. For the source language of our compiler, we use Python. And actually, to be a bit more precise, what we used is ChocoPy, which is a tight subset of Python designed specifically for compilers courses. So here's an example of a program that you can run using the compiler that we built. If you look closely, it's an implementation of a counter class with a single instance field. In this case, we called it index. And this index tracks the number of times that the inc method has been called, and some use of it in the REPL on the right hand. And the thing that ChocoPy does is it forces some restrictions and type annotations that you see highlighted here. And these restrictions make it easier to write compilers. ChocoPy was really nice to use, and it added a lot of structure to the course, especially in the beginning. And we found it really helpful. So if you've never heard of it, definitely check it out. It's great. And then to run the compiler directly in the browser without having to start a whole new server, we needed to use a target language that is supported by browsers. So we used WebAssembly as our target language. And the compiler itself was written in TypeScript. And we really liked using both of these technologies. And we think these are tools that will only be growing in popularity in the compiler's world. So with this web-based technology stack in place, the compiler was hosted on GitHub, and it auto deploys every time we push to the code base. And that was another nice thing about using this infrastructure. Our students were just able to link this compiler easily in their resumes and personal websites. And with this infrastructure in place and the students spending the first half of the course getting familiar with it, we are now ready for the whole class collaboration phase. As I mentioned before, in the second half, we started the whole class collaboration phase, and we formed groups of 3 students each. And every group started developing a single feature in the compiler. And we formed about 17 groups, and this is the full list of features that we added to the compiler. So that means at some point, we had almost 50 contributors to the same repository, which was very exciting. And the different projects reached different stages of completion. So we didn't end up adding every single feature to the final compiler. And that's what the merged column in the middle means. And as you may have guessed already, that many people contributing to the same code base meant we spent a good chunk of time resolving conflicts. But that didn't end up being such a bad thing. In fact, we had a lot of interesting interactions with the students and many valuable teaching lessons resolving these conflicts. And just to give you an idea of how these interactions played out, I'm going to walk you through 2 different problems we are faced with. The first one involves the dictionary strings and list groups, and the next one involves the closures and the named arguments groups. So let's start with the first one. If you're familiar with Python, Python has a bracket operator for lookup, and it's overloaded. This means that the groups that worked on the dictionary, strings, and lists all had to implement the bracket lookup for their features. And before the group project started, there was no code in the compiler for the bracket lookup. And we ran into a conflict when each group submitted one of these blocks that you see up here. And from each group's point of view, what they submitted was the entirety of bracket lookup. And the work the groups were doing naturally started overlapping and conflicting. So it made sense to come together and discuss a unified approach. In this case, during the merge, we settled on a switch case that you see at the top. And this switch dispatches on the type of the expression to the blocks of code that these groups defined. And this discussion happened both live in lecture and some of it asynchronously over GitHub. And there is something really cool that we noticed here, and that is all of these groups had different styles in writing this code. So let me zoom in a little bit on that. The list group at the bottom here chose the inline code generation for the bracket lookup, while the string group that you see at the top decided to create a WASM function to do the string indexing, and then they generated code for calling that function. This is a pretty classic trade-off for code generation for language with built-in data structures. And here the students created this juxtaposition organically and provided an opportunity for a lot of good discussion in lecture. Another interesting moment was when we noticed that the dictionary and list groups both used inline code generation, but the dictionary group did it in a helper function somewhere else in the compiler that we don't see right here. But the list group has this big block at the bottom that you see. And we prefer the style of the dictionary group. We think it makes for a clearer compiler, but we did not try to enforce any code writing styles. So both groups wrote code in a style that made more sense to them. But they got to see and live with a different option they could have made writing this code. And we were really excited when we saw this because it made some of the points that would come up in a software engineering class much more immediate and organic because students generated this scenario themselves. Here's another interesting interaction. We had one group implementing closures and higher order functions. So we could write something like the map function that you see here, and then use it like the example at the bottom. And we had another group adding optional arguments to functions with default values. And that's a pretty commonly used Python feature. And after merging code from both of these groups, both of the programs that you see produce the correct output. So that was great. But then we wrote another program. And we ran into a really interesting problem because this program requires the interaction of both of these features. And at this point, it wasn't clear what the type annotation or the representation is for a closure with an optional argument, or even which team would be responsible for figuring that out. And this turns out to be non-trivial because it requires adding a new kind of type and subtyping. So those two features in our compiler just interact poorly, and they produce frustrating type errors or sometimes just wrong answers. And what I just presented is only 2 conflict scenarios out of a whole list of them. And in our experience, resolving these conflicts often led to really good discussion and learning about compilers that happened very organically, because the students themselves were running into these interesting compilers questions and were motivated to find answers for them. We're teaching this course again next spring, and we have a few changes planned already. First, we're planning on giving the group projects more time. And we're also going to add some additional structure to the group projects phase, where we're planning on having alternating weeks, where 1 week students get to think about the design of their features and work on resolving conflicts with other groups. And the following week, students just get to focus on the implementation of their features. And that's it. Yeah, thank you so much. We have a lot of the resources that we used public. Our compiler and our course website and the experience report we wrote are all public. So definitely check them out. Thank you so much.
Thank you. Any questions? Right, we got one here.
Hi, this is Will. And my question is, first of all, I love this concept. So it's really cool that you ran this, and I totally support what you're doing. One concern I have is when you have so many different sort of slices of this global assignment, then I assume, each kind of sub-project may have a different kind of work, different level of difficulty, a different kind of concepts involved. And, I'm just wondering how you balance that of trying to make sure everybody has, to some extent, a consistent experience, so people come out of the course with, knowing similar things. And I know there's the individual projects up front. But I'm wondering if there's anything that you can do to try and make sure that regardless of which slice of the compiler somebody gets, they still have a certain shared experience of the concepts that they encounter.
Yeah, that's a really good question. One of the things that we're definitely considering is how to produce content that's interesting for all the groups, because that's definitely one of the worries once groups starting working on different features. And yeah, we're giving it a lot of thought, just how to thread the content so that every group cares about it. And then we have a very big definition for experience with compilers, and we're happy with people working on any side that touches on compilers, whether that's error reporting, front end, back end. So in that sense, we're happy with these groups.
Okay, great, thanks.
I saw Dennis, you had a question on Zoom. Do you want to ask that one while I get our next question in the room lined up?
Okay. Have you considered having some teams actually perform code reviews or design reviews on the work of other teams?
Yes, that is a great question. That is one of the things that we're planning to do the next iteration, because we noticed that we asked teams to write unit tests whenever they write features and sort of programs that illustrate that their features work correctly. But then once all of these features started to interact, people weren't thinking about other groups. So we thought that doing code review would be a good way to get everyone to think about any of the interacting features.
Great.
Yeah, that's a really good question. Thank you.
Hello. Hey, Yusuf, it's John from UCSD.
Hi, John.
Hey, I was wondering how you handled the cutover from their individual projects to a shared code base. Presumably, most people lost all their code.
Sure, yeah. The code, since we were all implementing the same core features, the code on a high level looked similar. So the base that we started with was the one that Joe and I wrote, which we would like to think it's the cleanest one, but maybe it wasn't. But it wasn't that hard of a transition for our students, just because they saw a lot of this code during lecture and it looked familiar.
Gotcha. Thanks. Hey, Yusuf. It's Michael here.
Oh, hey.
How much structure did you and Joe provide to students to resolve conflicts? Like in open source software, some people in a community can steamroll others to get their way.
Yeah, that's a really good question. We had a lot of approaches for resolving conflict, and Joe, definitely feel free to jump in on this. We had some time in lecture where it felt really productive to just have everyone right now discuss the different pros and cons of choices we can make. And sometimes it just made sense for us to make a small decision and then push it back onto the teams, and they just have to adjust to it. But yeah, overall, we did a lot of mob programming with everyone. Yeah, a lot of code reviews, of course.
See, thanks.
Yeah, and I'll just add that, Yusuf and I were actually the only people allowed to merge pull requests. So we took on the maintainer role. And so we forced API decisions on students. Students didn't really force API decisions on each other.
Oh, we got one more question. Maybe not planted.
Hi, I'm Paul He from the University of Pennsylvania. I was wondering, you talked a bit about conflicts between teams. Did you deal with conflicts within teams? And in the future, do you think it will make sense to have individual students be in charge of smaller pieces of the compiler?
Yeah, that's a really good question. Yeah, I guess there's sort of personal conflicts and then there's code conflict. And the whole time I was referring to code conflict. We really didn't get involved in any group personal conflicts. And we did have some people who chose to work individually just because during the pandemic, they were in a different place. Time zone coordination was difficult. But I think they lost a little bit of the software engineering aspect of the experience. But we definitely wouldn't be against it if that's what a student is comfortable with.
Yeah, I guess I just want to add to Yusuf's answer that we didn't, this is like the problem with liking good feedback, right? We were excited that groups thought that the groups were really awesome to be in during the pandemic. That's the kind of feedback that we got, that they actually had more community in this class than they had in other classes, because they had a group of 3 that they were assigned to work with. Most of them did. But it's really easy for Yusuf and I to listen to the positive feedback, and we didn't hear about any personality conflicts. That doesn't mean they don't exist or we shouldn't be figuring out how to do that better. But the groups did pretty obviously communal pull requests, and I asked in some cases who kind of did what, and most of the groups were all doing programming as a trio on a Zoom call. It seemed to be the way almost all the groups were working.
All right, I think we better leave it there for session 2. So thank you to all of our speakers this session. There's people who are ready to clap in here. They won't hear you, but. We have we have 19 minutes of a break on our end over here. If the speakers in the 3rd and final session want to hang around, I'll leave the Zoom call going. You can try out your screen share and all of that. And I'll be sure to come back in early enough to help you troubleshoot if there are issues. So I'll see you all back here in about 20 minutes. Eli, are you there?
Yes, right here.
Okay, we're
Can you hear me?
just,
Everything is
I'm
fine?
starting to hear people heading back into the session, so I'll give it another minute. I wanted to make sure
Sure,
you were ready.
sure.
So. All right, I think we can get started. So this is our third and final session of Splash E. First up, we have Eli Tilovich telling us about the Common Coder Scratch programming idioms. So Eli, go ahead.
Thank you for the introduction. So I'm Eli Tilovich of Virginia Tech, and this is joint work with Xinyu Long, who was my master student. He's since successfully defended his master thesis and now works for VMware, and also for Piratham Jacob Local. In 6.5 years that he'd been with me, I never learned to pronounce his name because Thai people, they go by their nicknames. He was always Karn and then Dr. Karn after he obtained his PhD. He is now a professor in Thailand. So this paper is about Scratch, probably one of the most successful educational programming environment. It encourages, it's a visual language. It encourages experimental and bottom-up approach to programming. Also, it's a great platform for CS education research. It has an online learning community where more than 50 million projects are shared. And its claim to fame is that Scratch encourages so-called communal learning, where usually students, pretty young students, they can explore projects accomplished by other students, and then they can remix their own project by basing them on some existing project out there. And that provides a great learning opportunity because you get to understand, other people's code, and you get to enhance them. And what we would like to encourage, probably a good thing, is to encourage people to remix projects in non-trivial ways. Just downloading someone else's project and changing the background color is probably not good for learning purposes. Well, so this body of shared projects has been studied, and it's known to suffer from recurring quality problems, but this project is about something else. But I would like to give you some background. When we first started looking at Scratch, and I had an NSF grant to study the issue of code quality in Scratch, and also to provide automated refactoring support for Scratch, we got a lot of pushback from the community because they said, well, worrying about code quality is counterproductive because Scratch is about is driven by constructivist learning theory, which encourages free tinkering, and once you start thinking about quality, then it's going to be disadvantageous to all the positive learning, basically provisions that that you find in Scratch. And then the way we were able to convince the community that actually quality is important with this paper, Understanding Recurrent Quality Problems and Their Impact on Code Sharing, is that we showed that when your code is of poor quality, it's less likely to be remixed, and the remixes are becoming less significant and not as conducive to quality learning. So we had a really large scale project. This is prior work. We analyzed more than 1 million Scratch projects. We found some code smells, and we proved that code smells hinder project remixing. And I'm not going to go into details, just to show you some takeaways from this prior work. So we conducted a large scale longitudinal data analysis, and we showed that there is some proneness to introducing smells, and when students gain more programming experience, their poor programming practices, basically the propensity to introduce code smells, remains in their source code. So, and then what this project is different. So we said like, well, a lot of people are talking about code smells and anti-patterns, but before you start talking about this, so maybe we need to study more what actually comprises idiomatic Scratch programming. What are the good coding idioms in Scratch, and how can we teach them more effectively to introductory students? So once again, so the this example which demonstrates what I mean by idiomatic code. So I already used something today. So for example, this is an example from Python when you are doing something with a list versus using a list comprehension. Yeah, so the code on the left is non-idiomatic, the code on the right is idiomatic, even though they're functionally identical, but we should promote that programmers, Python programmers, use the code on the right, right? So let's see. So let me give you an executive summary what this paper is about. We identify Scratch coding idioms from expert-written Scratch programming materials. So this paper presents a catalog of 11 Scratch idioms, which were gleaned from the top 5 Scratch books. Then we assess the prevalence of these idioms and study how they are used in remixes, right? And then we discovered that novice programmers can actually recognize and apply highly common idioms, and at the same time they rarely use many idioms which are used by experts. And certain idioms may help promote meaningful project remixing. And by meaningful, I mean where students actually write a lot of extra code in the remixes. And we think that this findings could be beneficial to both educators and learners, particularly those concerned with introductory computing education. Okay, so here are the research questions which drove this research. So we wanted to know what the common programming idioms are in the top 5 Scratch books. We want to see how common these idioms are in large, diverse data set of Scratch projects. And then question 3, how does the code change within the detected common idioms when projects are remixed? Okay, so here's our method. First, we compiled a canonical set of idioms. So we used the 5 top Scratch books, and we assume, well, I mean, if you write a book on programming in any language, you'd better consider yourself a seasoned programmer in that language. And so those are the books that we considered. And then that produced our catalog. So there was a process. So we put a systematic process in place where each identified idioms was discussed and eventually made it into the catalog. Please see paper for details how we actually did it. So we basically look for small, reusable, generalizable patterns that repeat themselves across different compile sources. Now, so then the next step was to assess their prevalence. And here we relied on this excellent tool called Litterbox, which is an open source tool where, the way we did it, so we analyzed 70,000 non-trivial Scratch projects, which came from different categories. So this Scratch website makes it really easy to find out what kind of projects you are dealing with. So there could be trending projects, contributed by so-called top programmers, or maybe even classroom studio projects. So they're all different categories, and you can pick and choose whichever project you need for your research as necessary. Okay. Now, let's see. So the way we detected this idioms, it's standard kind of compiler analysis. So you have an abstract syntax tree, you have a visitor which traverses this tree. It collects the necessary information to determine whether a particular idiom is present. You know, basically standard, the same kind of processes which are used by compilers and linters in particular. Okay. So let's see. Now. So the next thing So how we measured the actual code, how the code changes between remixes. So the code on the left is the original project. The code on the right is the same is the same idiom, but in a remixed version of this project. Okay. So in the original version, so this is a typical forever if idiom, and then there were 5 blocks of code within the if statement, and in the remix, so we find 7 blocks. So what this means that 2 new blocks were added in the remix. Okay. So, and we calculate all deletions, insertions, and value updates. And so the methodology is actually very simple. So everything is converted to formatted text, and then you just can determine a lot of things with a simple text def. Okay, so let me talk a little bit about our findings. Okay. So we identified, so research question number 1, so I identified 5 general and 6 scratch specific programming idioms. So the 5 general idioms, 2 of them are list related, and 2 of them are control flow related. Yeah, right. And then this repeat ask is not related to this 2 things. So then there were 6 scratch specific idioms such as change and clone, change and wait, repeat, change. They only make sense within the context of scratch. I mean, they would not, this kind of idioms do not exist. They don't have equivalents in other programming languages, at least in text-based programming languages. Maybe they exist in other block-based languages. That's something to be explored in the future. Okay, so here is an example, repeat change idiom. So it repeats a sequence of side effect causing blocks, position size, graphic effect. And this is from this Galaxy project. Another example, forever if, it continuously monitors a given Boolean condition. And this one came from Apple Boss Flights project. So this is how this idioms kind of look like, visually. Okay. Now, another interesting thing. So the prevalence of this idioms. So here I found something interesting. The top 3 idioms, we found them between 30 and 60% of all project idioms. The rest of the idioms that we found are actually much less prevalent, including some of them which occur in a teeny portion of studied projects, actually. And some of them, there are some interesting observations. Certain idioms, they're common for particular domains, such as change, wait, and repeat. I mean, they're common in animations, games, and stories, while forever if, it's highly common in games and tutorials, but less common in other types of projects. Okay. Now, research question 3. I mean, that was kind of interesting and maybe disappointing at the same time. So we studied, we didn't study all of the identified idioms. We only studied the if and forever if idioms as being kind of most interesting in terms of their advanced functionality. And we discovered that actually the majority of code changes in the remixes are deletions, right? And also, so there was something interesting about the insertion between forever if else versus nested if else. For some reason, the forever if else had twice as many insertion as a very similar idiom as nested if else. So an interesting tidbit here. Okay, so let me quickly discuss our findings before I'll entertain some questions. Let's see. So certain programming idioms that we found, I mean, they're highly prevalent, such as change and wait, repeat change, forever if. And most scratchers, both, I guess, experts and, regular Scratch programmers who contribute their projects to the Scratch website, they do recognize and apply these idioms. Now, at the same time, there were some idioms which were common among experts, but are actually used only rarely among scratchers in the wild. And I think this particular idioms, they present an educational opportunity for an intervention. I mean, if these idioms are mentioned in Scratch programming textbooks, but are not used in the wild, maybe educators can draw the attention of introductory learners to these particular idioms to encourage the usage of these idioms, right? So for some reason, the forever if idiom was associated with a high percentage of insertions, basically desirable remixing behavior, where when remixing projects, a Scratch programmer, a student is actually writing new code, right? And just to adapt this existing project for to satisfy the requirements of their project. Okay, so just to summarize our findings, so we identified Scratch idioms from expert-written Scratch programming materials. So we have a catalog of 11 Scratch idioms, and they are found. They came from 5 Scratch textbooks. We assess the prevalence of these idioms and study how they behave, how they manifest themselves in remixes. We recognize that novice programmers, they can recognize and apply highly common idioms. At the same time, some idioms are only known to experts and not as widely used by novice programmers in the wild. And certain idioms, they may help promote meaningful project remixing behavior, just writing a new code. And we think that these findings, they can be beneficial for introductory computing educators and learners. Thank you so much for your attention, and I'll be happy to take questions.
All right, thank you. Are there any questions? All right, I have a question. So oh, there was one, sorry, hand here. So.
Sure, okay.
Thank you for the talk. I was wondering, so these idioms are mostly composed of several sort of built-in blocks in Scratch, it seems. Do you think it can be reasonable to just add like a new built-in blocks that amounts to the same kind of functionality, and then maybe it will be easier to teach those?
Right, so maybe, yeah, that's an excellent question. So basically what you're asking, would it be meaningful maybe to build a library of common idioms, right? Where these blocks come together as predefined kind of components out of which you would be able to build projects, and thereby, I mean, if you don't have individual blocks, but if they already come as components, would it promote kind of better usage of this common idioms? And that's a very interesting idea. So one of the issues is that there was, kind of a lack of a meaningful procedural abstraction in Scratch. So they don't even, so procedures of functions, so they have an approximation of that. It's called a custom block, right? And it's not really as easy to use as it should have, because that would have been probably the right unit of encapsulation and abstraction in this library. And currently, there are several efforts across different block-based languages to improve the procedural abstraction in these languages, because maybe a good unit of sharing and distribution should not be an entire project. Maybe it should be a certain subset of this functionality, right? Maybe it should be, maybe the functionality should be shared at the procedure level, right? But for that, the procedure has to become kind of a first-class abstraction in Scratch, and it is not there yet. But your idea is definitely very interesting and worth exploring.
Other questions? Yeah.
Hi. So for those idioms that were not popular in the wild, I wonder, have you looked at how people in the wild express the same thing that experts express in their books? Because maybe what experts, like with the Python example, the code you had, which was non-idiomatic, looked pretty bad. But maybe for some of the idioms that we find in expert books, maybe there are also an alternative that is not that bad and might be actually a better idiom, but it just didn't happen to make its way into the book.
Yeah,
So I guess the question is, have you looked at how people express the same things that are expressed by non-popular idioms?
Yes, thank you for your question. Very, very interesting. Unfortunately, we didn't explore, this particular aspect of this problem because it was not part of our research agenda. But that would be a very interesting follow-up direction, and just it would be a very effective attempt, kind of, to bridge what people in the ivory tower, understand as, kind of common Scratch programming idioms, and what they decide to teach, versus a more kind of bottom-up approach, kind of to mine these idioms from, from existing code bases. But there is a danger here, because well, beginner programmers, they may not be the most effective users of the language, right? And if we mine their usage, it may not be the best usage of Scratch, only because they were able, it's very likely that they are writing non-idiomatic Scratch code, right? So we have to strike kind of the right balance. I mean, if there are some creative and interesting ways to express the same functionalities which are presented in the textbook, but for whatever reason are not commonly found in the existing Scratch code base, or is because beginner programmers tend to write non-idiomatic code. This issue is definitely worth of further exploration. Thank you so much for your question.
All right, thank you very much. So we've got our next talk coming up. It's a little bit of an experiment because it's pre-recorded. And I realized at the last moment that I don't want to touch the audio in this room because it did not work this morning. And if I touch it, I'm sure that will be reproduced. So Kevin is going to share the video, and Kevin, I'll start shouting if things don't work.
Yeah, no, thank you. That sounds good to me. I prepared this as pre-recorded just to hopefully get around any kinds of technical issues. I'll see if this works. Let me just share my screen.
Worst case, we can all just go off and watch it on our own and then come back. So
let me just make sure that I have the audio. So share sound set up, and let me know. Can I just get this to full screen? Let me know if this works for you guys.
Yep, we hear it. Thank you.
Perfect. Sounds good. Enjoy.
Hello world. My name is Kevin Dick, and I'm a PhD candidate in the Department of Systems and Computer Engineering at Carleton University in Ottawa, Canada. I'm eager to present our work entitled Machine Learning Pedagogy to Support the Research Community. Both myself and my fellow co-author and co-teaching assistant Daniel Kairolos are members of CUBIC, the Carleton University Biomedical Informatics Collaboratory, under the direction of our research supervisor, Dr. James Green. We are a collaboratory that focuses our research on the application of machine learning to diverse challenges in the field of bioinformatics, biomedical engineering, computer vision, and generally beneath the umbrella field of biomedical informatics. In this presentation, we describe our novel curriculum design to introduce undergraduate students to applied research through a series of course assignments and a competition amongst peers to inspire other educators. We describe the overall course structure and detail how the assignments were tailored to a selected open research question while developing student understanding of machine learning. For the selected COVID-19 related course-long problem of predicting which drugs might interact with specific proteins, we leveraged state-of-the-art tools for representing drug and protein sequences. We challenge students to develop unique solutions competitive with the current state-of-the-art models using reproducible notebooks and cloud-based computing resources, with the expectation that top-ranking solutions would be used to predict novel, druggable targets within the SARS-CoV-2 proteome to possibly treat COVID-19 patients. Excitingly, our experience ultimately resulted in the top student solutions being combined using a stacked classifier to create a publishable solution representing an actual research contribution. We highly recommend introducing undergraduate students to open research applications early in their program to encourage them to consider pursuing a career in research. Offered for the second time in the fall semester of 2020, an elective course entitled Introduction to Machine Learning under course code CISC 4996 was offered as an elective course to upper undergraduate students within the Systems and Computer Engineering department at Carleton University. The course was offered to 68 enrolled students in several engineering disciplines, including software, computer systems, communications, and biomedical and electrical engineering. The course assumed a number of prerequisites, including an undergraduate level of probability and statistics and knowledge of at least one programming language. The Python programming language was used throughout the course, however, experience in programming was quite diverse. Software engineers were clearly the most prepared at one end of the spectrum, and with biomedical engineers at the other having only an introductory programming course in their program. To assist all students equally, each of the weekly tutorials covered coding examples, implementing or demonstrating materials covered that week in the lectures. Also, accompanying each of the 3 assignments were skeleton notebooks within which students implemented their solutions and which greatly facilitated the benchmark evaluation of their work. This figure presents a conceptual overview of the course design and deliverables. The course is partitioned into 3 phases aligned with 3 assignment type deliverables. As part of Assignment 1 or A1, the students are taught and evaluated upon machine learning foundations. In Assignment 2, the students form N groups and are introduced to the selected open research questions and evaluated based on their ability to implement, train, and test a baseline model, allowing students to familiarize themselves with the programming framework. The students are also asked to provide an overview of their anticipated approach to their final solution. In Assignment 3, students then implement, refine, release, and document their final solution. The top K of N selected solutions, using a systematically evaluated measurement to baseline and the state-of-the-art, are integrated into a meta-model using ensemble method and are re-evaluated against the state-of-the-art. Successful results warrant open source release and subsequent publication with contributing student authors sharing an equivalent contribution authorship. Excitingly, machine learning methods can be applied to a wide variety of domains given a suitable representation, whether they are manually engineered or learned through deep learning, and by abstracting domain-specific considerations of a problem into the type of formulation amenable to a given machine learning framework. For our course offering amid the pandemic, we selected the highly relevant problem of predicting whether specific therapeutics could be used to treat COVID-19 patients. The fully online learning environment and context of a global pandemic prior to vaccine availability made this problem particularly enticing to students and motivated the curriculum adaptation. Facilitating much of this coursework was the then recently developed Deep Purpose framework. Most excitingly, the project's lead developer, Kexen Huang, notes that among the embedding methods exposed through the Deep Purpose API, the vast majority of combinations of embeddings have yet to be exploited to evaluate their impact on DTI or drug-target interaction prediction tasks, meaning that teams of students could each attempt a unique combination of embeddings and architectures as part of their individual solutions. The importance of such a framework cannot be understated. A critical component of this curriculum design necessitates a robust library developed by a domain expert or by the TA to abstract much of the low-level concepts into a numerical representation easily integrable in other machine learning frameworks. In leveraging this framework and providing minimum viable working solutions, students had access to a robust framework within which they could easily embed DTI pairs and feed them into the machine learning architecture of their choosing, for example Keras, PyTorch, Hugging Face, etc. The ability to train machine learning models and explore their associated hyperparameter space is often limited by available compute resources. To provide all students with an equal platform on which to innovate, Google Colab was used by all students for modeling and evaluation. This free cloud-based system provides standard development environments to all participating students. The democratization of such cloud-based hardware enables students in low computational resource environments to contribute to research initiatives in ways that they might not otherwise be able to. This platform also simplifies students' efforts to quickly get up to speed with a suitable development environment, complete with free GPU-accelerated compute resources. While ambitious, we expected that framing the assignment as a competition amongst their peers and to surpass a baseline set by one of the current published state-of-the-art methods would foster creativity and generate interest in research applications. Moreover, the suggestion that the work produced within the context of the course might eventually contribute to alleviating the COVID-19 pandemic and potentially save lives further motivated our students. The DTI predictors generated by students could be applied to predict candidate drugs that might be effective in treating COVID-19 patients. Emphasis on reproducibility ensured that resulting models could be leveraged by the community well beyond student coursework. Experientially, we gleaned several lessons from this work and summarized them here to support educators seeking to follow from our efforts. Lesson 1. Research experience inspires research interest. Anecdotally, following this course, some students considered pursuing research for the first time. Run in the fall of the terminal year of their program, this experience was offered at a late stage and would be more effective in the penultimate program year prior to students settling on a career in industry. From this experience, students realized that given a suitable library and cloud resources, they could contribute to interdisciplinary challenges with relative ease. Lesson 2. Focus on an interesting, well-formulated, and abstracted problem. The reality of the ongoing COVID-19 pandemic galvanized interest in biology-related problems related to the pandemic. However, students have a specific information technology or electric and computer engineering background, in contrast to a generalized interdisciplinary background. The use of the Deep Purpose API was key to generate effective data representations to permit non-biology students to contribute to a biology-focused challenge. Experientially, the generation of a reusable library or framework by a TA is itself a highly rewarding research contribution. Lesson 3. Provide a baseline and encourage creativity. Providing students with a baseline working model permits everyone to succeed. While some students will aim for a minimum viable solution, likely due to other commitments or limited capabilities, they should have a positive experience. Complementarily, the high achievers should be encouraged and enabled to go well beyond the baseline solution. By setting the baseline solution as one of the current state-of-the-art models to build upon and compare themselves, students are provided with a tangible and empowering sense that they can advance the frontier of knowledge. And finally, tempering performance expectations. While not a lesson per se, a final note on running a student-centric competition as part of machine learning pedagogy is to temper one's expectations of the outcomes. While research advances have been achieved through competitive environments, such as the effect of the Kaggle Live leaderboard that encourages continual innovation beyond the best practice, it should not be assumed that framing a student-centric research competition will necessarily yield noteworthy results. In conclusion, upper undergraduate pedagogy represents a unique opportunity to introduce students to the research community and excite them with the potential to generate actual research contributions by leveraging their creativity in generating notable solutions. Machine learning course educators, as with their students, are expected to benefit from the experience of tailoring machine learning projects to relevant applied research projects. We encourage machine learning educators everywhere to follow from our example and incorporate applied research projects within their curriculum design. Thank you all for your interest in our work.
And with that, I'm happy to take any questions.
All right, thank you.
No worries.
Any questions?
Oh, one sec. I have a video just auto playing right now. One sec.
Okay.
Give me 2 seconds. One second. I don't know where it's starting. I have a few tabs open. Sorry for this 1 second.
It's no problem.
I'm so sorry for this. I don't know. I have so many tabs open. I can't find the one that's Oh, 1 second. It was on a full screen on another tab. Sorry about that. Okay, I'm good. So sorry.
That's okay. We couldn't hear it the whole time, so it was just you suffering. So
okay, yeah, no, I'm good. Sorry, I had a video playing, auto playing, but it was on a full screen on another desktop.
All right. Are there questions in the room or on Zoom? I have a question. So we heard in the previous session, I don't remember if you were there, about a class that was working together on compilers, but instead of doing sort of separate projects, they were collaborating on pieces of the same one. I wonder if you considered that kind of model for machine learning. Do you feel like that it adapts to that, or is it better to have these small groups on their own models?
Yeah, a lot of the motivation of this work actually was originally inspired from a previous course or like a previous research contribution from graduate students under the Burkhard-Rost lab at TUM in Germany. So basically this was a master's run course for specifically bioinformatics students to run on an international competition. There was only 16 students in that course, and they had kind of subdivided, they'd framed the whole problem. This was back in 2013. They'd framed the whole problem in a similar way, abstracting away a lot of the specifics of the problem, breaking up these 16 students into groups of 4 that all kind of worked cohesively or like collectively, and then each kind of subgroup went off and produced their own solutions. And that's kind of the way that we had approached it too. We stuck with groups of 2, just because I kind of mirrored a lot of what previous courses within the programs offered, just team-based group projects in kind of a smaller setting. We could have kind of changed the granularity of the size of the groups if we thought that maybe perhaps larger groups then could have come up with different results. I don't think there's a definitive size that made a lot of sense. What we were really excited about though was we had about 68 was kind of the final student count. We ultimately started with about 78 students in the group, and we thought that pairs of 2 would allot for a much broader set of like diverse ideas, and individuals pairing off together would often focus on specific kinds of architectures of their interest. So some people were more focused on classical machine learning using random forests or SVMs and the likes, things that they learned earlier in the course, while others who were a bit more inspired by new transformer types technologies kind of paired off in that way. So if we had a large collection of many students, I think we wouldn't see such a diversity in the types of solutions considered. And it also allowed kind of pairs to focus on things that they were most interested in. But I do think that there's a lot of value in trying to see if collectively, student groups all try different approaches and then, hone in on the one that seems most successful. But that ended up ultimately being the work of us, the teaching leadership, to say, well, we evaluated all your models, and of those who provided solutions, well, the ones that succeeded the most were, certain folks in the transformer space or in CNN space and so on and so forth. So it was more on us to evaluate models accordingly. But perhaps that kind of curriculum design where perhaps you have everyone collectively trying different things out, and then perhaps focusing on those that seem more promising to then go on and produce their solutions afterwards. So yeah, I feel like there's a lot of value in evaluating these kind of things kind of iteratively.
Great, thank you. Dennis had a question. Do you want to ask it yourself, Dennis?
What was the range of experience of the students? I mean, what did they know going in?
Yeah,
did you have, real hackers, or did you have, data scientists, or did you have domain experts?
We had a few students that were very surprising. I mean, one in particular, or like one pair of students in particular had read up. They had done a lot of previous research experience. I feel like at the undergraduate engineering level, a lot of the stuff that we discovered is most students don't have exposure to research problems or like applied research problems. And there were a pair of students that did. They had at least 2 or 3 years, and some of them had internships at Google and so on and so forth. So they were coming in with a very robust, set of experiences and frameworks to their name that they could easily rehash or reapply. So we did have some. Those are the high achievers that we referred to in the video. And then on the other complete end of the spectrum are those who are coming in with, basic programming experience and at least the backdrop of the machine learning foundations and the tools that we had provided earlier on. So it was quite diverse, but it was also very exciting because since it was kind of in a competition-like environment and still online, people were, speaking to one another and co-supporting one another. So we ended up with a quite diverse set of solutions and some much more creative on different ends, and really it depended on what people were most comfortable with. We had students come in with completely novel encoding methods that they had rehashed based on the framework we had provided, and we didn't expect that at all. I think there's just a lot to glean from these kinds of framings for both the students and for the teaching leadership.
Good.
All right. Thank you very much, Kevin.
Yeah, thank you very much.
So next up, we've got our in-person talk for the session. So we're cycling through formats here. Those of you on Zoom, can you see Braxton? I know it's far away, but Braxton is there. Braxton,
hi.
Your mic is on. Can people see and hear Braxton?
Can they see and hear me? Oh, I closed the chat.
Oh, I see some thumbs up. Okay, I think you're good.
Okay, sweet. Hi, everybody. So I'm Braxton, and I'm here to talk about office hours. But before we begin, is this on? Please be on. 1 second. I did off and on it, of course. No, I would really like control, actually. Sorry. 1 second. Does it need to be clicked in?
I think I'll make it redo it. If you're willing. Yeah. Thank you very much.
Thank you very much. Thank you. Okay, hello, I'm back. I'm Braxton, and I'm here to talk about office hours. But before we begin, I would like to acknowledge that this work was conducted on the traditional, ancestral, and unceded territory of the Musqueam people. Now, I'm joined by Noah, Elisa, Megan, and Reed, and together we teach a third-year software engineering course at UBC. It's a pretty big course. We have 17 TAs and over 250 students per term. And those students get together in teams of 2 and make a full stack web application. It's broken into 4 project deliverables, and they work on it slowly. And of course, they have questions. And when they have questions, they come to the TAs. And what they used to do was they'd grab a pen that looks like this Expo marker. They would write their names on the board in a queue. They wouldn't sanitize the pen or their hands. And they would, okay, that's not allowed anymore. So we've switched to this. This is the online queue service. It was made by some folks at the University of Illinois, Urbana-Champaign, and I'd like to say thank you. This has been very helpful for us, not just in running the course, but also it's given us some new insights into office hours. For example, we now know that 64% of students are coming to office hours, and we know that on average, a student is coming 5 times with a pretty high standard deviation of 8, meaning some students are coming never, and some students are coming dozens of times. This is built on top of some other instrumentation that we already had in the course, and that's our auto grader. So the students collaborate in a GitHub repo, and they push to the origin. Every commit is automatically intercepted by our auto grader and graded using a pretty comprehensive test suite. The commit can be either ineffective or detrimental, meaning their score went down. It could be an improving commit, meaning their score increased. And their commits are graded automatically, whether or not they request feedback. So with commit information down to the millisecond, actually, and visit information down to the second, naturally, you might try and ask some questions like, when do students attend office hours? How do office hours influence grades? Are the long visits helpful? And does independent work between visits correlate with grades? So let's start with the easy one. When do students attend office hours? So you can see here, each blue bar is a measure of unique students in the term, and we have the deadlines in black. And of course, the dramatic peak right up to the deadline that you've all seen before. This one isn't too surprising. So next we wanted to know, when do students attend office hours in relation to when they're working? And we can use commits as a proxy to when they're working. If you're making a commit, you probably are working in and around that time. So you have a visit to office hours, and then you count the number of commits made in 1 hour buckets after office hours or preceding office hours. And we do this in this visualization for every visit to office hours, overlaid 24 hours in each direction. We see a dramatic peak in the middle, meaning that students are visiting office hours right in the middle of when they're working. There's a decline about 12 to 15 hours on either side, and I would guess that that's when people are sleeping. And then 24 hours out again, there's another small peak. So why does this happen? If I had to guess, it's because we have 18 hours of office hours available all throughout the week in a variety of times. As soon as a student has a trouble that they need help with, they can come to office hours because they're assured that there is a session very soon. So students attend office hours around the times they are actively developing. Now, how do office hours influence grades? So as we already said, a commit can be an improvement commit, an ineffective commit, or a detrimental commit. Now, ineffective isn't as bad as it sounds. It could be a refactor, or it could be adding tests. But here we see the proportions of these commits for all the commits in the entire term. Next, we checked for a baseline the last commit preceding a visit to office hours. And we saw what were the proportions for that. Now, for the last commit, before visiting office hours, students have a higher proportion of improvement commits. So students are already working on a solution before coming to us for help. They're already making some progress. And then for the first commit following office hours, it's an even higher proportion of improvement commits. So nice, we're doing something. We're helpful. Commits directly after and directly before a visit to office hours have a higher proportion of improvement commits. Now, controversially, perhaps, we don't have time limits on our office hours. Most of the time, it's a 20-minute visit, but sometimes it goes all the way to 2 hours over there at the end, which is the maximum length of an office hour session. And I want to know, is that helpful to anybody? So we group commits following a visit to office hours, again, with improvement commits, ineffective commits, and detrimental commits. And these are all the commits made in 5 hours after a short visit in office hours. We did end up seeing that the longer your visit in office hours was, the more likely you were to be making an ineffective commit. So you're spending over an hour, it's much, much more likely to be an ineffective commit. And this makes sense because we know that students who have a larger total sum time in office hours have a lower project outcome in the end. If you're the kind of student who is going to have a negative project outcome and are struggling with the course material, you're likely to be asking the question of your TA, can I have 5 more minutes? So longer visit to office hours precede a higher proportion of ineffective and detrimental commits. Now, you go to office hours and you come back to office hours. What happens in the intervening time? You can measure this in 2 ways, time and commits. We saw that globally, students are coming back to office hours after a week, and they're making 3 commits in that time. However, students with a negative project outcome, under 50% on the final project, are coming back every 3 days. And in that time, they aren't even making the full commit. It's just half a new commit's worth of work. Whereas students at 100% are waiting a full 2 weeks before they come back to us and making 3 commits in that time. That's 2.5 more opportunities to get autograded feedback, 2.5 more opportunities to get feedback from your partner, 2.5 more opportunities to get feedback from yourself. So we see that students with a perfect project outcome have more time and more commits between consecutive visits to office hours. Now, the next question that a person might have is, what do I do with this information? And I'll tell you what we're going to do. So we know that we asked the question, when do students attend office hours? Around the time they're working. So let's keep scheduling office hours all around the week. No matter what time zone a student is in, it would be nice if as soon as they run into a problem, there were office hours nearby. Next, how do office hours influence grades? Positively. So let's share that with the students. There are still many students who don't come to office hours at all. And for those students who are struggling, we can tell them we know that we're helpful. Are long visits helpful? So we know that long visits negatively correlate with a proportion of improvement commits. But now that we have that visibility into office hours, we can flag those kinds of students and we can say, hey, there are alternative methods for us to help you, like a recitation or a tutorial or additional notes. And lastly, does independent work between visits correlate with grades? And we saw that students who do well take longer and contribute more before coming back to us. And that's good for the students to know because it can inform how they build habits and they can pull that into their process, but it's also useful for us. So now we can, as we can see students and how much they contribute before coming back, we have the opportunity as TAs to say, how about you make 2 more commits before you come back to me? I know it'll be good for you. So that's what we're planning on doing. And thank you for listening.
All right, do we have questions? I have a question. Oh, wait, nope. Oh, that's an old question. Okay. Yeah, so my question was, could you go back to the slide where you were looking at the long office hours?
Yes, I can. This one?
Yeah. Oh.
This one.
This one, yes.
Mm-hmm.
So you're comparing the students who go to the long office hour appointments against the students who go to short office hour appointments. Did you compare those students after their long office hours appointment to the same student before their long office hour appointment? Because you might find something different. It may be that they still struggle compared to the students who get the short appointments, but they might be better off than they were before.
I'm not sure if we did actually. I would have to go back and check, but that's a good one.
There may be very small numbers. I mean, there was like 1 2-hour appointment, so it's kind of tricky. But interesting. Other, oh, here we go. We have one.
Can you go to the next slide? Yeah, this one. So I was interested in this partially because the correlation seems a little like all over the place. Because like what I would expect is people who spend either a lot of time, like if people are spending a lot of time at office hours, that's almost usually like a sign that they're struggling. If people are spending no time at office hours, then it's usually bimodal of either they're really struggling and not coming, or they don't know about it, or they're just doing fine and they don't want to visit at all. And I was wondering to what extent that like that was reflected here. Like, is there even a normal distribution of like the people who spend medium amounts of time at office hours do fine, and then you find grades, maybe grades like on like the grade average decreasing at both ends? Is that kind of reflected here? Not.
Well, our grades are quite affected by the ceiling effect.
Right. Yeah.
So I'm not sure I'd be able to confidently answer that.
Right. Well, I guess this is long visits. This is not. I guess maybe what I'm really asking is, did you do any statistics on total visits to office hours and how that correlates with the project outcome?
Sorry, could you repeat the question?
Did you do any statistics on total visits to office hours as opposed to length of duration of visits to office hours?
We did
and then correlating that with project outcome?
Yes, we did. We saw it looked very similar to this.
I see. Okay. Good to know. Thank you.
Dennis has a question. Dennis, I'll let you read it again.
That's good, because I have some argumentative things about this too. What kinds of help strategies are available to students besides just office hours?
Okay. So immediately there is Piazza, which is asynchronous. They also have scheduled meetings with their teaching assistants. So they have mentors who will be following their progress. And of course, there's the autograder feedback, which has various levels of feedback for the students. And that's what we have immediately, like right now, implemented.
Okay. Back in my undergraduate days, I knew a chemistry professor who he was in charge of the freshman chemistry program. And freshman chemistry was always a disaster, right? You never had enough TAs. You had a lot of people who struggled with chemistry. And he started, just massive amounts of kind of structured technology to actually help people in small ways get over some of their issues, right? Small exercises. I think for this sort of stuff, like, a little programmed instruction where you have a worked out example with missing steps, and they actually have to say, oh yeah, what goes in here, what goes in here, what goes in here? Because a lot of the problem that people have of grasping some of the concepts, and in software engineering is definitely the case, is that they're lost, right? They haven't gotten into the pattern yet, but they need something more structured to actually get them into the flow of what they're actually supposed to be working with. How do you do an effective check-in in GitHub? That kind of thing. Now that you could diagnose with an individual session with the teaching assistant, but it would be good for to kind of mine some of the things that the teaching assistants have learned and have used in one-on-one sessions and kind of make that available. The second thing I think of is actually having help from other students in the class. Have some students volunteer to help some of the other students, because they don't hear the request for help in the same way that the faculty or the TAs do. Just thinking.
Am I back? Yes. Okay. Yeah. No. I guess we do have some tutorials, but I really do like the idea of having more of those and finding ways to figure out which tutorials students might need to return to through the autograder. So I think that is one of the things we could be working on. Yeah.
Yeah. Keying tutorials to autograder is like that. That should be easy, right?
Yeah. Ideally, but students find surprising ways to fail tests in creative ways that are complete. Like it looks like one failure, but it is the root cause is something else completely. But I guess that's a whole thing.
Yep.
Oh, we have one more question. Yep.
So I once did a similar project on metadata of people watching lecture videos. And one thing that was really interesting in seeing how this data changed over time, sort of like the one you had earlier across the semester, is people get backed up, right? They start off good, they're watching, the lecture roughly a day after it comes out, and then slowly it starts to bunch up. They're watching 3 lectures at once, they're waiting a week until after the lecture has gone out. And one idea I always had was trying to, if you had access to some data like that, to try and reach out to students based on that, if you could identify when they're falling behind. Like, I think this concept of, as you mentioned, finding students who are struggling by, say, long office hours is one thing. But like more generally, have you thought about how to, like other ways you could use this to identify students who are struggling based on when they're working on a certain assignment, or like other struggle indicators, especially when it comes to, like, I think people being okay in the beginning, but then falling off as the workload increases over the semester.
Hello, am I back again? Yes. Well, I might pass this one to Noah, actually, one of my collaborators, because they've had a lot of thoughts on this. I believe. Noah, are you with us?
Yeah, I am. Yeah, this is something we've been really interested in, like finding different metrics which can indicate why students are struggling, or identifying them early to us. Not just using office hours, but also using how students interact with Piazza and other course resources. And it's become more of a like important issue, I guess, now, because we don't have strict deadlines in the course. So it used to be like, if a student was falling behind, we could immediately find this out because they would fail to submit for some deadline, or their score would be so low for this deadline. But now that we don't have strong deadlines, we only have like real observability into like what their grade is going to be at the very end of the course. So it's like important to kind of find other insights into how a student might be struggling based on like changing work patterns, like if they're going to office hours a lot and then suddenly they stop, or they have this upward trajectory and then they stop, because we don't have that like intermediary feedback that we used to from these checkpoints. Because although the checkpoints do exist, we don't force the students to be entirely finished at that checkpoint. We let them do kind of remedial work after. So even if a student has like a low grade, they could remediate it. We don't know for sure if it's like an absolute case of struggling, or if they're going to remediate it later.
Great, thank you very much. Let's thank Braxton again.
Thank you.
All right, and our final talk, let me stop sharing over here. We've got our last talk, and thank you very much for the crew from Singapore for staying up through the night with us. So.
Hello, I'll just share my screen. Okay, so hello everyone, I'm Samyukta. With me is Professor Martin Hens from the NUS School of Computing. And together we've been working on Source Academy, a learning environment used to teach first-year computer science students functional programming. I'm sure that most of you may have already heard of Source Academy from previous talks, but if you haven't, let me go through it again. But before I go, so welcome to the last talk. Don't worry, it's going to be short. I hope you enjoy. Okay, so in their first year course, computer science students from NUS are regularly required to complete programming assignments that we call missions quests. And they do this on Source Academy, which is a learning environment that contains many modules, one of which is the sounds module. So over the past year, Prof. Hens, I, and Ko Shanghui, who is our co-author who isn't here right now, we've been working on developing the sounds module. And while doing so, we noticed that the sounds module uses a very different style of audio processing than other existing audio processing libraries. And we call our style functional audio processing. And in our paper, we explore how it works and how it creates teachable moments for students that are learning functional programming. So let me take you a bit background of audio processing. So audio processing is a great pedagogical tool to teach functional programming concepts. It's extremely engaging for the students because we can instantly hear the results of our work. And to our knowledge, most audio processing tools make use of a model called digital signal processing, which is the dominant conceptual model today. In digital audio processing, audio signals are stored in arrays and streams, which can then be transformed additively by combining them, and they can also be transformed subtractively as well. Now, that is the dominant model, but our sounds module actually uses something called functional audio processing instead, which represents sounds as continuous wave functions. So for example, if we wanted to create a sine sound, the function would look like this. It is possible to transform these wave functions as well, additively, as we're going to examine later on. Only at the very last stage, when a digitization function is called, are samples of the wave function temporarily stored in an array, which will be converted to an actual sound. But otherwise, throughout the process of constructing the sounds are represented as wave functions. And we do this because it's simpler for students to understand. They're first-year students who may not have much prior experience with programming, and so may not have knowledge of arrays or streams. And so with functions, everyone can understand how sound works and can manipulate them much easier. So how do we implement this in Source Academy? So although as stated before, A sound is essentially a function. Students have to make use of another function called make sound to create a sound, as you can see on the slide right now. And this is in order to account for the duration of the sound. The bolded part is to ensure sound discipline, which is basically saying that after the duration of the sound is over, the final function must return 0. And after the sound is created, it will then be made audible by a digitization function. So this whole part of ensuring sound discipline leads to a teachable moment about the importance of data abstraction. Make sound will always guarantee sound discipline. And so it's much easier for students to use this function, and it's more convenient for them to use this function instead. I thought we'd do a demo over here of how to create a sound. So let me just take you to a sample program. Okay, so here we have the make sound function being applied on sine wave. I'm going to play the sound for you now. Please let me know if you can't hear it by any chance. So that was a sample sine sound lasting for 1.5 seconds because of the make sound function. Going back to the presentation. So we also have additive composition operators that can be used. We have two major ones that I want to present today, which are simultaneously and consecutively. As the name suggests, they allow students to make two sounds overlap or append one sound to another. And students are actually asked during one of the early sound missions to come up with this code by themselves. And they would then later use this code in later missions. There's another teachable moment in the constructions of these functions. Students have to remember to always ensure sound discipline, which, if you remember, is making sure that after the duration, the sound returns 0. And this can be extended to other programming structures, where it's important to always keep in mind when you're writing functions for them, when you're writing programs for them, that certain properties must always be maintained. There's also a teachable moment about the importance of composition in programming, because this shows that application domains typically come with domain-specific composition operators. Again, I thought we'd do a little demo of how simultaneously and consecutively might sound. So here we have two sine sounds. The constant consecutive represents the two sounds being played after each other, as you're going to hear. And the sound simultaneous is how they'll sound simultaneously. You could hear a little bit extra after that. That's because one of the sounds, as you can see, has a longer duration than the other. Of course, you cannot have sound without mentioning music. Some of the missions involve students making sequences of notes as determined by Western music theory. If you've learned Western music, you may have heard of the terms major scales, minor scales, arpeggios, and so on. And we make students actually create functions that would generate the sequence of notes for these scales. But not everyone has knowledge of Western music notation. Not everyone has knowledge about music. So for them, to even out the playing field, we introduce something called the MIDI system. This is a table that essentially shows the relationship between the MIDI system and Western music notes. Essentially, the MIDI system represents musical notes as integers. Every increase in 12 MIDI notes corresponds to an octave, which is equivalent to doubling the frequency in hertz. For those of you who know more about music, you can say that the difference between two MIDI notes is the same as a semitone. And to mimic scales, we will use interval sequences of MIDI notes along with starting notes. So for example, a major scale would be represented by a starting note, and then consecutive intervals of 2 MIDI notes, then 2 others, then 1 other, etc. And of course, for this, you need to convert between Hertz, and MIDI, and Western music notation. And to do so, we students can make use of the functions over here that are given to them. And this is another teachable moment on the power of abstraction, because students realize they don't need to gain an in-depth understanding of Western music theory when they can just simply trust these transformers to do the work for them. Another little demo about a major scale function over here. This is ideally something like what a student can construct. This is the function major scale. You can see that we use letter name to MIDI note over here, which is one of the transformers. And this is this should play the C major scale. So that students would also be required to construct similar functions for harmonic minor scales, melodic minor scales, arpeggios, and so on. We also take this opportunity, since we've got music involved, to take advantage of rhythmic structures to talk about recursion. We base our rhythm system on konakol, which is the art of creating rhythms to different vocal syllables like tak, the, me. You may have heard it in instances of, for example, Carnatic music. And within such a rhythm, there can be several repetitions of patterns of syllables. So for example, a konakol rhythm could go something like takina dimi tom, takita tom, takita tom. You can hear that there are repetitions over there. And we take advantage of this property to represent each syllable as an integer when we're representing rhythms. And then we define a simple rhythm as a list of integers. A rhythm in general is recursively defined as either a simple rhythm or a list of rhythms, or a pair whose head is a rhythm itself and whose tail is the integer representing the number of times that particular rhythm should be repeated. So if you can see the example over here of the simple rhythm and complex rhythm, you can see that there's a sequence of 0, 1. There's a pair first with the list 0, 1, 2, and then the tail being the integer 3. That indicates that 0, 1, 2 should be represented 3 times. So students are actually asked to design functions that would convert complex rhythms to simple rhythms. And afterwards, they'll be asked to assign sounds as well, each distinct integer. And so this is another teachable moment on the part of the importance of language design, because you can see that we routinely invent new formal languages as required by the application domain when we want to make things more complicated, when we want to go beyond just playing notes consecutively one after another. And that is the end of our presentation. Of course, we're going to continue working on refining our functional audio processing methods. Currently, we're exploring parallelization of the digitization process. We expect significant speedups with the parallelization, but overall, we've received very positive feedback from students about the sounds modules. A lot of students say that they enjoy using it as a tool to learn about functional programming. We have a sounds contest called Game of Tones, where students try and create their own music using the functions given to them by Source Academy. Many of them actually create covers of popular pop songs or video game music, and that is one of the highlights of the module. And we therefore think that functional audio processing is a very powerful pedagogical tool. But just wait a minute before you go. We thought that to end the presentation, we'd actually give you a taste of what our students have used the sounds module for, and a little song that, so Marcus here has created a cover of a popular song using the Source Academy sounds module that you may or may not recognize. Enjoy. So thank you for coming and thank you for listening to our talk on the Source Academy Sounds module.
All right, thank you very much. All right, thank you very much. Ooh, why do I hear myself? Are there any questions? Well, first I'll applaud you for rickrolling an academic conference. That's pretty impressive. I had a question about the representation you chose for repeated patterns, or repeated rhythms.
Yes.
Yeah, the pairs. Why did you choose to put that in a pair rather than to create, say, like a repeat function that would repeat a list some number of times? I may not understand the conical representation well enough to know, but.
Professor Hens, would you, do you want to take this question? Or?
Well, the exercise here was to transform one representation of the rhythm to another. So we just chose the canonical list representation as a simple rhythm, and then constructed more complex rhythms also as a data structure. So it was sort of a finger exercise in I guess, list processing.
I see. So the actual implementation the students would do to do that translation is essentially the repeat function and an append,
yes,
list append.
Yes.
Okay, thank you. That clears that up. We have a question here.
Hi, awesome talk. I was wondering if you've thought about introducing other audio processing frameworks or languages, like at Max MSP, for example, because I'd imagine it could be cool for a student to see the same program implemented in this, textual functional style, as well as say like a visual data flow style, so as to better understand the relationships between programs and different paradigms. That might be a cool exercise if you thought about it.
I think we need to be honest here and emphasize that this style of functional audio processing, as we call it, is limited to additive sound processing. So basically, filters that you usually have in the usual audio processing tools are not available. So you need to basically additively construct sounds from bottom up, from sine waves. So all what you have heard are sine waves added together. That makes for a very simple framework. It lets you construct sounds from first principles, and without any data structure such as arrays or streams, but it has severe limitations. So you can't really build filters with this system.
Okay, thanks.
Are there any other questions? All right, I think we'll leave it there. So thank you to all of our speakers, especially those of you who had to stay up late. Thanks everyone who attended Splashy in person or remotely. I hope it was a successful year. I hope maybe to see you in the future in person at a conference when we can all travel safely and easily. So, thanks everyone.